Hi friends, today I'm going to teach some basic concepts of chemistry from Ncert, and this is going to be line by line. And I know that most of the students don't get Ncert, but actually I should say this, that Ncert has written the best way. In the best way it has been written the chapter. And the thing is that it is very important for competitive exams that you thoroughly understand Ncert. And before also I did a video on the living world in biology, the first chapter, so you can also check out if you want that. This is a series which is going on, that is the crash course which is going on, but here I will explain everything and I will deal with every type of questions which can come in the exam. So please be with me, and today I'm going to teach the whole Ncert line by line, and that too with MCQs, and if the all types of problems that could come in the examination. So let me start this. So this is chemistry. Yeah, the first is there is some introducing lines, but these are not so important, but let's read this thing. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. So actually this chapter is very important. Actually this is completely about all about the basics of chemistry, and I think that if you will understand this chapter thoroughly, you can understand everything, all the other chapters which is there in the 11th and 12th standard of chemistry. And you know that this solution chapter, the the second chapter of class 12 chemistry, that is also completely related with this chapter. So let's get started about this chapter. Yeah, so chemistry as we understand it today is not very old. So this is the development of chemistry I'm teaching now. Discipline. Chemistry was not studied for its own sake, rather it came up as a result of search for two interesting things: philosopher's stone, Paris, which could convert all baser metals, example iron and copper, into gold, and elixir of life, which could grant immortality. So people in ancient India already had the knowledge of many scientific phenomenon much before the advent of modern scientific phenomenon, which much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and laterochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe. After a few centuries of alchemical traditions which were introduced in Europe by Arabs. So what next is written that other cultures, especially the Chinese and Indian, had their own alchemical traditions. These included much knowledge of chemistry process and techniques. The ancient India chemistry was called Rasayan Shastra. So these are not so important, but still I'm reading this. uh, then this is Rastantra, Ras Kriya, or Ras Vidya. So these are the names which is known by Indians, ancient Indians. Okay, So it included metallurgy, medicine, manufacture of cosmetics, then glass, dyes, etc. Systematic excavation at Mohenjo-daro or in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked big bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro, gypsum, and cement has been used in the construction work. It contains lime, sand, traces of CaCO3. This is actually important. This CaCO3, it contains these things. Then Harappan's made faience and a sort of glass which was used in ornaments. This can come in the questions. Then they melted and forged a variety of objects from metals such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. So now we knew that tin and arsenic is used to make copper more hard. Then a number of glass objects were found in Maski in South India in 1000 to 900 BCE and Rastinapur and Taxila in North India, which is 1000 to 200 BCE. Glass and glazes were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technologies for extraction of copper and iron were developed indigenously. Now, according to Rig Deva, uh, tanning of leather and drying of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black published ware of northern India could not be replicated and is still a chemical mystery. These wares indicate the mastery with which kiln temperatures could be controlled, and Cortelius Arthashastras describes the production of salt from sea. The vast number of statements and materials described in the ancient Vedic literature can be shown to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta disc and painted grey pottery have been found in many archaeological sites in North India. Sushruta Samhita explains the importance of alkalis. The Charaka Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc. The sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Now these all are written how they just get these things. So you just need to read this once because it's not so important, but still you should not leave anything. Okay, so these are the things which just once you read. Next I'm going here, which is important things, and these are also that same thing how it just came. So here see uh, these particles here, this thing, just a second. Here, the concept that matter is ultimately made of individual building blocks. See, this one, building blocks, appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanda, born in 600 BCE, originally known as the name Kashyap, was the first proponent of the atomic theory. This atomic theory. He formulated the theory of very small individual particles, which he named Parmanu. So in India, atoms are known as Parmanu. Okay. Next, comparable to atoms. He must authored the he authored the text Vaisheshika Sutras. According to him, all substances are aggregated from a form of smaller units called atoms, which is Parmanu. Okay. Then, which is eternal, indestructible. These lines also important, which is eternal, indestructible, spherical, suppressible, and in motion in the original state. Okay. That this individual entity cannot be sensed through any human organ. Kanda added that Kanda is another person who added that there are varieties of atoms that are as different as the different classes of substances. He said these Parmanu could form pairs of or triplets among other combination, and unseen forces cause interaction between them. He conceptualized this theory around 2500 years before John Dalton. So this is the thing. So in India this was done 2500 years before from John Dalton. So this thing only makes us proud that so nice that we got it first. Next, Charaka Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metals is clearly discussed in Charaka Samhita. Extreme reduction of particle size is termed as nanotechnology. This thing you should remember, that it is known as nanotechnology, the extreme reduction of particle size. Then Charaka Samhita describes the use of Vasma of metals in the treatment of ailments. Nowadays it has been improved that Vasmas have nanoparticles of metals. After the decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medicinal system of 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continued to exist, but it too declined gradually. It took about 150 years for Indians to learn and adopt new techniques. Then, during this time, foreign products poured in. As a result, traditional techniques gradually declined. Modern science appeared in Indian scene in the later part of the 19th century. By the mid 19th century, European scientists started coming to India and modern chemistry started growing. So this only happened in India. Okay, so they came and then modern chemistry started growing. From the above discussion, you have learned that chemistry deals. So these are all the histories that we got here. Then from the above discussion, you have learned that chemistry deals with the composition, structure, properties, and the interaction of matter, and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter, that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weight, and perceive these entities? Atoms and molecules. Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? We will get the answer of some of these questions in the unit. We will further describe how physical properties of matter can be quantitatively described using numerical values with suitable units. So these are all written in the NCERT, that what it is going to do. Next, here some important points are there actually. Importance of chemistry. Okay, so what are the importance of chemistry? Here there is written, chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of a computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life saving drugs for natural resources. So here some importance are there, and makes possible synthesis of such drugs. Some of these drugs are cisplatin and taxol. So which drugs are written in the your NCERT book, that is only important, because no questions come from the outside of anything. Suppose these type of questions which is like right about the drugs and all. So these things are important, and this is cisplatin and taxol, which are effective in cancer therapy. So these are effective in cancer therapy. The drug azeti, which is azithromycin, is used for AIDS patients. So this you should remember, because this have chances in coming of in examinations. Okay. Next, chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principles, it has now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymers, metals, etc. These industries contribute in a big way to economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, which is chlorofluorocarbons, then responsible for ozone depletion in stratosphere. So you should remember this thing, and this is, I think you have read in the school also, that this CFC, this has caused ozone depletion in the stratosphere and have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large scale production of chemicals, and synthesis of new exotic materials are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. Now, let's go for the nature of matter. You are already familiar with the term matter from your earlier classes. Yeah, this is the thing. Now, tell me the definition of matter. Matter is something which occupies space and have mass. This is the thing which we have been reading from kindergarten, so this is so easy for everyone, I think. So see, from your earlier classes, now anything which has mass and occupies space is called matter. So here definition also has given. If somebody has forgotten this thing, then please remember this thing. Then everyone around us, for example book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of states of matter. Now let's go to states of matter. Okay, states of matter also one thing which we have been reading since like fifth class or fourth class. This is so easy thing. So this is what again? Solid, liquid and gas. These three are the states of matter. There are three states of matter, and these are these things. The constituents particles of matter of in these three states can be represented as shown in, okay, figure. Let's go to the figure. Which figure? Oh, it's not here. Yeah, here. See this figure. This figure is what? This is solid, this is liquid, and this is gas. This we know actually. Solid, suppose we consider, let us consider something solid. Okay, solid is pen. Okay, your pen which you are holding, that is solid. A liquid is H2O or water, and gas can be anything. You're using deodorants, that is also gas. So I've given example also. So this is deodorants. Okay, completed. Next, let's go to where we were there. Yeah, so the constituent particles of matter in these three states. Okay, I read this thing. Then particles are held very close to each other in solids. Yeah, this we know. Why solid is unbreakable? Like means many solids are unbreakable. It needs a lot of force to it so that it could be broken down. So I think like there are a lot of solids. Suppose okay, this pen or anything which I think you have holding of this pen or any pencil or anything like that. So you need a lot of force to break it. Why? Because they are closely packed. This thing you need to understand, and that too in an orderly fashion. Okay, this thing you will completely, and what happens inside a solid packaging and all these details you will read in the 12th class first chapter, solid state. Okay, then in liquids, the particles are close to each other but they can move around. So this only happens in the liquid case, that they are close to each other but they can move around. Okay, so suppose and it has flowing consistency. Okay, like suppose we'll take a glass of water. Okay, if we have water in this, then suddenly what happens, this glass fall down. I think this example you can I think you can keep in your mind. This example is very easy, and this water, all the water is now flowing down. So this is the thing. But if the in this glass there would be a bunch of panes or bunch of flowers which is solid, then if we have put it, but it would not break its size or anything. It couldn't change its shape. This is the thing. uh, so the thing is that, let me erase this. Another thing I'll explain here. Yeah, so next thing which I'll explain is that it's not happening. Some error has happened, I think. Yeah, okay. So so here what happened is that see, solid is something which cannot be breakable, or this or it cannot change its shape, or it cannot be sprayed everywhere like any time anything. unless and until temperature or pressure is applied to it. Okay, that's the thing. Okay, if you'll apply temperature or pressure, that is another level of thing that I'll explain later. Also there, here also it is there. And another thing is the liquid. What happens in case of liquids, when you suppose a glass of liquid is that a glass is there you put some water, then you're changing it to a ball. So what is happening is that the glass of water, the liquid, it is changing its shape. It doesn't have a definite shape. That's the thing. Next, if we'll go to the glasses, what happened in case of glass, sorry, I'm telling in case of gas, yeah. So gas, when we spread it, it completely, like, it sprayed all over your room. Suppose let's take the example of deodorants. Okay, when you're spraying deodorant, what happen is that your whole room is like or room freshener or anything like that, when you're just spraying it, what is happening is that whole room is just getting aromatic. So that's the thing, that's the exact meaning of these things. It doesn't have this also doesn't have any definite shape. Okay, next thing, the particle are far apart as compared to those present in solid or liquid states. Oh, here in gas. Okay, and their movement is easy and fast, and this only happens. And because of such arrangement of particles, different states of matter exhibit the following characters. Okay, see, here are some characters also given. Like solids have definite volume and definite shape. Liquids have definite volume but do not have definite shape. Okay, this thing, I've said these things also. Solids have definite volume and definite shape. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Okay, next next line is, yeah, gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. Okay, next is that these three states of matter are interconvertible by changing the conditions of temperature and pressure. I think I should explain this to you nicely. So see, what happens here is that suppose here is solid, I'm writing like this, solid, then I'm giving it some heat. Okay, then what is happening, it is changing into liquid. Next, when I'm giving some heat to liquid, it is converted into gas. Okay, and the reverse process also there. So gas, when I'm cooling it, the opposite thing when I'm doing to this, it is converting into this liquid. And when liquid is cooled down, then what happen is that it converts into solid. So this I can give a nice example of this. What example it can be? Okay, I'm telling you this example. The example is that suppose let's take ice. Let's take the form of water. Okay, ice when heated up, it converts into H2O, the liquid of water. Okay, it converts into water, the liquid form. Then we heat it again. What happens? It converts into the vapor form. Okay, vapor form. When this vapor is cooled down, it converts into water, and when this water is cooled down in the refrigerator or something like that, then it converts into ice. Okay, this is the exact thing that I wanted to explain. So I think you have got it, what I was trying to say. Now let's get back to NCRD. On heating, a solid usually changes to a liquid, and the liquid on further heating changes to a gas or vapor. Yeah, this only I said. In the reverse process, a gas on cooling liquefies or to the liquid, and the liquid on further cooling freezes to the solid. That only happens. So classification of matter what happened is that what is written is that in class 9 you have learned that at the microscopic or bulk level matter can be classified as mixture or pure substances. Yes, we knew this. And then these can be further subdivided as shown in figure 1.2. So let's first see this thing. Yeah, and this is the figure 1.2. What happened here is that matter, yeah, so matter is divided into mixture and pure substances, right? These matter has these two parts, mixture and pure substances. Then further mixture is again divided into homogeneous mixture, this is homogeneous mixture, and heterogeneous mixture. Okay, so homogeneous mixture and what is heterogeneous, I will everything I'll tell you. Then pure substances, pure substances also subdivided into elements and compounds. So it is again subdivided into element and compound. So these are the things which is actually divided, matter is divided into these parts. Now let's go get back to the text. So a mixture contains particles of two or more pure substances which may be present in it in any ratio. Hence their composition is variable. Pure substances forming mixture are called its component. Many of the substances present around you are mixtures. For example, sugar solution in water, air, tea, etc. are all mixtures. A mixture may be homogeneous or heterogeneous. This is another. We have seen that division, the subdivision, that is homogeneous or heterogeneous. A homogeneous mixture, the component completely mix with each other. This is known as homogeneous mixture, where the component completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture, and its composition is uniform throughout. So see, suppose a sugar solution is taken. See, a sugar solution is taken, and what happening is that in this container there is sugar and there is water. Or suppose, let me be more see, suppose there is a Coca-Cola bottle, and if you'll take from the bottom, the taste will be same, and if you take from the top, the taste also will be the same. Okay, so this is known as homogeneous mixture. Then what is heterogeneous mixture? Heterogeneous sugar solution and air are the examples of homogeneous mixtures, we got it. Then heterogeneous mixture, the composition is not uniform throughout, and sometimes different components are visible. This is the thing. So for example, mixtures of salt and sugar, grains and pulses along with some dirt. So yeah, see, nice example it has given. Often stone pieces are heterogeneous mixture. See, suppose we mix sugar, salt, or grains and pulses or anything like that, then what happens is that the mixture is not same. Suppose a bottle is there and I have put grains and pulses, then every time the solution must not be the same. So this is only known as heterogeneous mixture. So you can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Now yeah, this we knew before also, that we can separate these mixtures also. And then let's go to pure substances. So what are pure substances? Pure substances have characteristics different from mixtures. So it is completely opposite of mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water and glucose are some examples of pure substances. So these are pure substances. So water is completely a pure substance. Glucose, gold, silver, copper, all these examples are pure substances. Then glucose contains carbon, hydrogen and oxygen in a fixed ratio, and its particle are of same composition. So this is the thing. See, I think you might ask me a question that why, yeah, this is in a fixed ratio, that here also having carbon, hydrogen, oxygen, which forming a glucose. But when we are taking the example of a salt solution or a sugar solution, which is a mixture, that is also contain water and sugar. So how this is same thing? But yeah, the same thing is that here the word you must focus on this word, that this is fixed ratio, that are not fixed. You can take how much sugar, any quantity of sugar in a solution, in a water or anything, to make a mixture. But here you need a particular, means a particular, a fixed ratio of carbon, hydrogen and oxygen to make this glucose. That's the thing. Okay, and its particles are of same composition also. That's the thing. Then hence, like all other pure substances, glucose has a fixed composition. This can come as a question, because this is actually, it's like making your brain a little bit confusing. So for that reason, it can come as a question that glucose is a pure substance or a mixture. So you should take it as pure substance, because it is in your NCRT and you should read it. Okay, next is also its constituents, carbon, hydrogen and oxygen cannot be separated by simple physical methods. This is another thing. You have to see this thing, that in a heterogeneous mixture or a homogeneous mixture or a mixture actually, and a pure substance, what is the main difference? Main difference is something that it is in a fixed ratio and that is not in a fixed ratio. And another main thing is that we can separate it in by using physical methods. But in case of this mixtures, we sorry, I'm a little bit, yeah, again I'm telling, what happened is that in pure substance we cannot separate it by physical methods, but in mixture we can separate it using physical methods. So this is another major difference between these two. Next thing, pure substances can further be classified into elements and compounds. Uh, Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous class, I think it is, yeah, previous classes. However, you will be studying about them in detail in Unit 2. Yeah, Unit 2 we have the chapter named as structure of atoms. There we can read it very nicely, that what exactly all the properties and all the details about atoms and molecules and everything. Next, sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. These are all elements. Okay, they're all atoms. They're all atoms are of one type. Means, see, suppose we take the atom of oxygen, and so all the atoms, sorry, we suppose we take element that is oxygen, then all the atoms inside it is similar. But if we take an atom of sorry, if we take the element hydrogen, there inside all the atoms would be different from the atoms of oxygen. Means the properties and everything, the size also may differ. So these are the things which makes it different. Next, however, the atoms of different elements are different in nature. What I said now only, this is only written here. Then next, some elements such as sodium or copper contain atoms as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. Okay, so this is the thing. Now for example, hydrogen, nitrogen and oxygen, so these are the thing which forms molecules. Okay, which is like two. Okay, I can show you one example. See, this is like we write O2. We don't write it as we don't this is correct, but we cannot write it as O. This is wrong. Okay, these are in molecular form, H2, then N2. Okay, these all are in their molecular form there. Okay, so next thing is gases consist of molecules in which two atoms combine to give their respective molecules. this is illustrated. See, here it is illustrated also. So these are the atoms of different elements, and here this is the H plus H, which is H2. That is a molecule of hydrogen. These are the atom. Two atoms come together to form a molecule. Okay. So there then two or more atoms can come to form a molecule, but here these cases are having two atoms. Okay. Next thing is that when two or more atoms of different elements combine together in a definite ratio, the molecule of a compound is obtained. Moreover, the constituents of a particle of a compound cannot be separated into simpler substances by physical methods. This is another thing also. When two or more atoms of different elements combine together in a definite ratio, this is known as compound. Uh, Moreover, the constituents of compound cannot be separated into simpler because these are chemical process. This cannot be converted into by physical methods. See, suppose we combine H2. The best example is this one. Suppose we have H2 and we have O, oxygen O2. When you are combining these two like this, okay, just yeah. When I am combining this two in this ratio, it is giving us H2O. Okay, this is the 2:1 ratio. So this is a compound. Okay, so and this compound cannot be means again separated by physical method. Okay, so this is the thing. Next, they only can be separated by chemical methods. Yes, that can be separated by chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. So let's find it, which figure. Yeah, here. So here it is given that C, water molecule has shown that thing. The next thing is that carbon dioxide molecule. This is CO2. So these are known as compounds. Okay, and these are like carbon dioxide molecule and these things. Next is carbon atom. Thus the atoms. Oh, here I, yeah, just. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. So the ratio differs, and the ratio differs, then only different types of molecules create. So that's the thing. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. Yeah, that is another thing, because the particles of the and the new compound which is formed by these elements, the element has different properties, and this can also differ. The compound can differ, like hydrogen have different properties, but when it gets into H2O to form this water, it has another property. So we cannot say that both things can have same properties. No, this cannot happen. It could differ. Okay, and it differs also. That's the thing. Also the properties, this I read. Then for example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with a pop sound and oxygen is a supporter of combustion, but water is used as a fire extinguisher. So this thing which this NCERT has written here, you need to understand this again. So I will understand you, but see, this is actually very important thing. Here it is telling that water is an amazing thing. Why? Because it is formed by hydrogen and oxygen. Hydrogen is something which burns. Hydrogen, when we burn it, it burns with a pop sound also. Sorry. I think you have experimentally you have did this thing before also, or if you have not done, then you will do. so no worries. But that happens. And oxygen, as we know, it's a fire, it's a supporter of combustion. Okay, it's a supporter. Without oxygen we cannot combust anything, we cannot make a fire. Like, I think you have done this experiment before, that where we close the container completely, where we do not allow oxygen, and combustion doesn't take place. Yeah, this only is important, and oxygen is important for combustion. So this thing also here tells us that but water is used as a fire extinguisher. So it's a completely opposite property which we got from their combination. Okay, so this only happens. Now, properties of matter and their measurement. So let's start with physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories. That is, one is physical property, another is chemical property. Okay, so such as color, physical properties such as color, odor, melting point, boiling point, density, etc. And chemical properties are what? Like composition, combustibility, reactivity with acids and bases. These are all properties. Next, physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic uh, reactions of different substances. These include acidity or basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. Next, here, following sections, we will learn about the measurement of physical properties. Measurement of physical property. Quantitative measurement of physical properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number that denotes a meter, the unit in which the length is measured. And this is what, see, earlier two different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which originated in France in late 18th century, was more convenient, and it was based. So what is more convenient? It is metric system. Okay, it just went up again. It is this metric system, and this is more convenient. Okay, next is, and it was based on the decimal system. This is based on the decimal system. Late need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. Now, this system is known as the International System of Units, that is SI. The International System of Units, in French, Le Système International des Units, abbreviated as SI, was established by the 11th General Conference on Weights and Measures, which is CGPM, from Conference General des Poids et Measures. So this is the full form of this. Then the CGPM, as an intergovernmental treaty organization created by a diplomatic treaty known as this. See, this is here it is written about this, and then here, yeah, meter convention. which was signed in Paris in 1875. So these all details you just need to little bit keep in your mind, otherwise, because it could come in the examination. So just remember this, that this treaty was signed in 1875, and the conference and the CGPM, the full form of that, just remember these things, the basic things, just remember that. The SI system has 7 base units. This thing also you need to keep in your mind, that it has 7 base units, and they are listed in the table. Now I'll read those things. These units certain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. So what are these? These are length, mass, time, electric current, thermodynamic temperature, amount of substance, luminous intensity. There are 7 quantities, which is important. Okay. Next thing is that symbol for quantities. These are of length. Symbol for length is this. Then mass is m. Then time is t. Electric current is I. Thermodynamic temperature is T, then amount of substance is N, and luminous intensity is I. There is a subscript which is V. So this is the exact thing, this is the exact meter. And the SI units, this is for length it is meter, then for mass it is kilogram, for time it is second, then for electric current it is ampere, then the thermodynamic temperature it is Kelvin, and then amount of substance is mole, then luminous intensity is candela. That's it. And here are the symbols given. Okay, so just remember these things, because this is really important. These are the 7 base physical quantities. Okay, next here, the definition of the SI base units are in the table 1.2. So here are the definitions, and these definitions are really different from what you know. Like for example, the unit of length, the meter. What is the definition of meter? The meter is the length of the path traveled by light in vacuum during a in time interval of 1 by 299 792,458 of a second. So this type of now let's read the kilogram one. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. So they are trying to explain, and if you will google this units also, the definition of these units, you will get these answers only. So these are the definitions which are done by the scientist, and these are the standard definitions type things. So I don't think these are very important, but still read just read once and keep in your mind, just keep in your mind, and it will be fine. The SI system allows the use of prefixes to indicate the multiples or submultiples of a unit. These prefixes are listed in table 1.3. So let's go to prefixes. What are prefixes? Can you tell me what is that? That is actually milliliter or milligram, or these are the prefixes. See, these actually you need to keep in your mind, because this is actually important. When you will solve question, that is needed. These are not asked directly, but when you solve question, it is needed. Okay. See, another thing is here, nano. This nano question can come, that nano is what. So some people some like students write that it is not a unit, but it's actually a prefix. Okay, it's not a unit. Okay, so that's the thing. So they write it as unit. That's the thing you need to keep in your mind. This is a common mistake actually done by students. So let's go down next. What here? Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight may vary from one place to another due to change in gravity. You should be careful by using these terms. This is actually important. So mass and weight differ from each other. Weight depends on gravity and mass doesn't depend on the gravity. It's just the amount of matter present in it. So like suppose for example, if we go to moon, suppose our weight is different in moon and it is different from earth. So suppose where weight is something different, that will be something different from, because their gravity is different. For that reason it is different in the moon and it differs in the earth. Okay, that's the thing. But mass doesn't differ. Mass is the actual and the amount of substance, of amount of matter that is present in it. Okay, that's the thing. Next is that the mass of the substance can be determined accurately in the laboratory by using an analytical balance. Okay, so analytical balance helps in determining the mass. Okay, then the SI unit of mass is given in, as given in table 1.1. Yeah, we have seen that. Then is kilogram. Okay, so 1 kilogram equal to 1000 gram is used in laboratories due to the smaller amounts of chemicals used in the chemical reactions. Okay, that's the thing. Because when only kilogram, if it would be there, then that would be a little bit difficult for us. But gram helps us for this thing. Okay. Next is volume. Volume is the amount of space occupied by a substance. It has the units of length q. So in here, yeah. So in SI system, volume has units of mq. But again in chemistry, chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or dmq, that is units. Okay, these are the units. Next, so this is centimeter or decimeter. Then it is a common unit liter, that is L, which is not an SI unit, is used for measurement of volume of liquids. Okay, so volume of, this is meter cube or centimeter cube. These are of volumes which is of solids. Okay, like solids or cuboids. So we measure those things with the help of that. But these are the liter cube. This is the volume which is that unit is useful in measurement of volume in liquids. Okay, so 1 liter equals to 1000 ml. 1000 centimeter cube equals to 1 decimeter cube. Okay, that's the thing. See, one thing I missed out, this is the analytical balance. Okay, so this is the analytical balance. See, this is the beam, this is the pan and such things. Okay, so next thing, so this is only written here. Now let's go to the next page. What is this? Yeah, in the laboratory, the volume of liquids or solutions can be measured by graduated cylinder, burette, pipette, etc. A volumetric flask is used to prepare a known volume of a solution. These measuring devices are shown in figure 1.7. See this one. So this first is here, see, burette. Then second one is pipette. Then this is graduated cylinder where we can measure the liquid and take it. Then this is volumetric flask. Okay, actually these are all important things which are required in a laboratory and we can measure the volume. Next we are going to density. The two properties mass and volume discussed above are related as follows. Now this is, see, this is mass by volume. Density, the means how we can write it, it is mass by volume. Then density of a substance is its amount of mass per unit volume. The this is the definition. Then so SI units of density can be obtained as follows. SI unit of density equals to SI unit of mass divided by SI unit of volume. So So we know SI unit of mass is kg, and SI unit of this volume is meter cube. Okay. Let me decrease the size. Yeah. Next, this unit is quite large, and a chemist is often expresses a chemist often expresses density in gram centimeter minus 3, so to the power minus 3. Then this is where mass is expressed in gram and volume is expressed in centimeter cube. So density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Next, temperature. There are three common scales to measure temperature, that is degree Celsius, degree Fahrenheit, and Kelvin. Okay. So here it is, Kelvin. Here K is the SI unit. The thermometers based on these scales are shown. Where? Figure 1.8. Let's go there. Yeah, this is. So this is Kelvin scale, this is Celsius scale, and this is Fahrenheit scale. Okay. Here the measurements are different. Okay. And the boiling point of water is also different. See, in Fahrenheit case, the boiling point of water, which is 100 degrees Celsius in Celsius scale, that is 212 means 212 degree Fahrenheit, and it is 373 Kelvin, and that is actually a standard thing. Now we can see this. There is a formula. See this thing. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water respectively. The Fahrenheit scale is represented between 32 degree to 212 degree. The temperature on two scales are related to each other. Now this is the equation which you need to remember. Actually, I think you have remembered it since 7th standard or 6th standard also. We have read this thing, that degree Fahrenheit, just a second, let me do like this. Yeah, so degree Fahrenheit equals to 9 by 5 degree Celsius plus 32. This way we can convert degree Celsius to degree Fahrenheit and vice versa. Next thing, the Kelvin scale is related to Celsius scale as follows, like this. See, this is the again another relation which we can convert degree Celsius to Kelvin and the vice versa. Kelvin equals to degree Celsius plus 273.15. It is interesting to know that the temperature below 0 degree Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale negative temperature is not possible. This thing also is important because it can come as MCQs. So this point you should mark it. Next, uncertainty in measurement. Many a time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers of conveniently and where that is, yeah, and present the data realistically with certainty to the extent possible. These ideas are discussed below in detail. See this scientific notation and these all things. So now I'm going to read this this green box. Okay, the reference standard. After defining a unit of measurement such as the kilogram or the meter, scientists agreed, this thing actually important for that reason only I'm reading this. So scientists agreed on reference standards that make it possible to calibrate all measuring devices. For getting reliable measurements, all devices such as meter sticks and analytical balances have been calibrated by their manufacturers to give correct readings. However, each of these devices is standardized or calibrated against some reference. The mass standard is the kilogram since 1889. It has been defined as the mass of platinum iridium. Then this is cylinder that is stored in an airtight jar at International Bureau of Weights and Measures in Sevres, France. Uh, PTIR, which is a platinum iridium, was chosen as for this standard because it is highly resistant to chemical attack and its mass will not change for an extremely long time. Okay, this is so simple. So they kept this as the standard, and this is highly resistant for the reason. This reason also you need to remember in this, that why they kept, as it is highly resistant to chemical attack and its mass will not change for an extremely long time. For that reason only this platinum and iridium was chosen, and it was for this standard. Okay, then scientists are in research of a new standard of mass. This is being attempted through accurate determination of Avogadro constant. Okay, this Avogadro constant. What is Avogadro constant? That's a number which is like 6.023 into 10 to the power 23. That's the number. Next, work on this new standard focuses on ways to measure accurately the number of atoms in a well-defined mass of sample. One such method, which uses X-rays to determine the atomic density of a crystal of ultra pure silicon, has an accuracy of about 1 part in 10 to the power 6. This thing also you need to remember, but has not yet been adopted to serve as a standard. There are other methods, but none of them are presently adequate to replace the platinum iridium cylinder. No doubt changes are expected within this decade. The meter was originally defined as the length between two marks on a platinum iridium bar kept at the temperature of 0 degree Celsius and 273 point, which is 273.15 Kelvin. That is 0 degree Celsius is equivalent to 273.15 Kelvin. In 1960, the length of the meter was defined as 1.65076373 into 10 to the power 6 times the wavelength of light emitted by a krypton laser. So, although this was a cumbersome number, it preserved the length of the meter as its agreed value. The meter was redefined in 1983 by CGPM as the length of path travelled by light in vacuum during a period during a time interval of 1 by 299792458 of a second. Similarly to the length of the mass, length and the mass, there are reference standards for other physical quantities. Okay, so these are the things. Next is scientific notation. So this chapter is actually like this physics first chapter, that is units and measurements. So I'll teach that chapter also. I am teaching physics, chemistry and biology, everything. So please subscribe to my channel, and this is a marathon, or you can say it's a crash course or whatever it is going on. Okay, next I'll do it every day. I will upload these things. Okay, next one chapter. Then, as chemistry is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers, of chemist has to deal with numbers as large as this. See this number. And then for the molecules of 2 gram of hydrogen gas, or as small as this. See, I cannot read this much big number. It is this number. So the chemist deals with these things. Gram mass of a hydrogen atom. Next, similarly, other constants such as Planck's constant, speed of light, charges on particles, etc., involve numbers of the above magnitude. Then, it may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operation of addition, subtraction, then multiplication or division with such numbers. You can write any two numbers of the above type and try any one of the operation you like to accept as a challenge, and then you will really appreciate the difficulty in handling such numbers. For that reason, scientists do a great effort. For that only they are scientists. Okay, this is the thing. Now this problem is solved by using scientific notation for such numbers. For this reason, to make it a little bit easier for them, we have scientific notations, so we need to study this. Okay, so for such numbers, that is exponential notation, in which any number can be represented in the form n into 10 to the power n, where n is an exponent having positive or negative values, and n is a number called digit term. Okay, which varies between 1.00 and continues, and 9.999 and it continues. Okay, next, thus we can write 232.508 as 2.32508 into 10 to the power 2. Okay, as it is in exponential form. For that reason, in scientific notation, note that the while writing it, the decimal had to be moved to the left by 2 places, and the same is exponent 2 of 10 is in the scientific notation. Similarly, here 0.0016 can be written as 1.6 into 10 to the power minus 4. Okay, this thing. Now here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific term. So this I can explain you what actually happening. Here only let me explain. Okay, see, if we are doing such thing that we are changing this, see, suppose this is 2.52. Okay, I've taken this digit, so I want to move it to this left side. So what will happen is that I will do like this: 2.252 and here into 10 to the power. Here what I can do, can you tell? If I move it this side, the left side, then what I have to do? Can anybody tell me this thing? Yeah, I have to add one 10 here. Means here, see, this thing I have to do. When I am moving it, okay, another example I am taking. I am just making you comfortable. See, here also it is written this thing, that 232. See, here this thing I was trying to do. See, when I am writing this 232, just yeah. So when see this, so let's take this example only. Then I will explain my example. See, 232.508 as this. See, when it is written as this, then 2 plus 2 is done. Okay, that thing I was trying to explain you. Plus 2 is added in the exponential form. Not that 10 plus 2 is done. That will be 12. That is not the correct answer. Okay. So when it is moved to left side, when this value is moved to left side and this happened, then 10 to the power 2 means plus 2 is added here. Okay, had been see, here also it's written that, and same is exponent 2. But when we do this thing, let's take this example. What is happening here? We are taking this, the zeros are taken down here. See, now first point this, then this, then this, then 1 2. I mean, what it is happening is that we are taking, see, 0.00016. So first the 0 was there, then we took it to this side, 1, then 2, then 3, then 4. Here now the point is. So we have come with the 4 steps. So if we have come 4 steps ahead, means to the right side, then what will happen is that into 10 to the power minus 4 we have to do here. So exponential form we have to do minus. Okay, that's the thing. Okay, so I hope you have understood this, and I don't need my example also to explain this thing. This is very simple. Actually, you have been doing this since like kindergarten, I think. Okay, next. While performing mathematical operation on numbers expressed in scientific notations, the following points are to be kept in mind. That is what they are. That is first, see this multiplication, division, then we have addition and subtraction, then significant numbers. This is something different, this one. So multiplication and division, I think you should go to NCERT and you should see this thing. These are really easy to understand. See what is happening here, they are just taking it like this, and then they're putting they're taking the 10 or the exponent form differently, then they're doing this multiplication very easily. Then what is happening here, we are adding this to, okay, this one and this one, so we are separate, we are making it separate, and then we are adding it to this. Okay, then here this much happened, and then as I said, they are moving to left, so they are adding another. Okay, then plus 1. If we are moving towards left, then we are doing plus 1, that is most important. Okay, then we are doing plus 1, and if we are moving to right, then we are doing minus 1. That's very simple. Left plus 1, right minus 1, that's it. Okay, it's really easy to understand. So you have to just go to the NCERT page and then follow these things. Okay, next, significant figures. Significant figures is very easy. This is all about, this is also there in the physics. Okay, first chapter, the units and measurement. Now I'm going to teach this one also. Okay, so every experimental measurement has some amount of uncertainty associated with it because of limitation of measuring instrument and the skill of the person making the measurement. For example, mass of an object is obtained using a platform balance and it comes out to be 9.4. On measuring the mass of this object on an analytical balance, the mass obtained is 9.421. So this thing. So which is more accurate? That is this. Okay, this is more accurate. Okay, this value is more accurate. This is not so accurate. Okay, next, the mass obtained here, mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. Therefore, digit 4 placed after decimal is the measurement by platform balance is uncertain. Okay, the uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. So significant figures are meaningful digits which are known with certainty plus 1, which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. Thus, if we write a result as 11.2 ml, this thing, we say the 11 is certain and 2 is uncertain, and the uncertainty would be like plus minus 1, and unless otherwise stated, an uncertainty of plus minus 1 in the last digit is always understood. Okay, next, there are certain rules for determining the number of significant figures. These are stated below. Now I'll explain all the rules. Okay, these are what? All non-zero digits are significant. So the first rule is that all non-zero digits are significant. Okay, so this is the thing, that all non-zero digits are significant. So let me show you what exactly it means. So see, actually here example is there. See, 285 centimeter. There are 3 significant figures, and in 0.25 ml there are 2 significant figures. So wherever there will be 0, we have to ignore that. Okay, so like see 285. Okay, this thing, yeah. So 285. So this is 3 significant figures. 3SF. It's not working. Just a minute. Yeah. So suppose there is a number which is 5 to 8. Suppose I'm taking this number. This is 3 significant numbers. But if I'm taking a see this 500, then this is 1 significant number. We have to ignore these zeros. Okay. If a number is non-zero, then it is significant. Okay. This means next, zeros preceding the first non-zero digit are not significant. Such zeros indicate the position of decimal point. 0.03 has one significant figure and 0.0052 has two significant figures. Okay, so the zeros are here, the zeros are there. So like after and before, we have to follow this thing. Let's see, it is showing that this digit 0.03, so it is one significant figure. Why? Because we are ignoring the zeros. Zeros are not significant. Okay, okay, next is this one, 0 or 50, this is 5 2 is written, and this is 2 significance. So again we are ignoring the zeros. Why we are ignoring the zeros? Because it is representing the decimal point. Okay, for that reason. Next, zeros between two non-zero digits are significant. See this thing, but we have to keep in our mind that if a zero is like this, see like this, or if a zero is like this, then we need to ignore these zeros. But if a zero is like this, like 20005, then we need to include in our significant numbers. So significant digits, so this belong, so it means this is 1 2 3 4 5, so it is 5 significant figures. We cannot ignore these things. If it is after or before, if the zeros are located after or before the mean digits, then it is ignored. Okay, that's thing. Next, the zeros, so it has 4, this digit has 4 significant figures. Next, zeros at the end of or right of a number are significant, provided they are on the right side of the decimal point. See, for example, this 0.200 has 3 significant figures, but it otherwise the terminal zeros are not significant. If there is no decimal point, for example 100 has only one significant figure. Yeah, what I said earlier, that thing only. But another twist is there. What's the twist? That is, suppose see, I'm taking this example. See, check this example out. Suppose we are taking this 100. See, here this example has been given, has only one significant figure. So if we consider this is one significant figure, but if I'm considering this digit, that is 0.100, so this is 3 significant figures. Why? Because after decimal it is there. Okay, it is there after the decimal point. For that reason it is significant. Okay, that's it. Next, has 4, so this has 4 significant figures. Such numbers, as you see here also it is mentioned, this thing I'll show you. Wait, yeah, this thing. If a digit is like this, 100, then point, then 0, this is 4 significant figures. Okay, that's it. Because it is after the decimal point, the zeros can be counted and it is significant. Okay, that's the thing. Okay, the reason is mentioned here. 100 as 1 into 10 to the power 2, 10 to the power 2 for one significant figure, and if it is 1.0, then it is 1.0 into 10 to the power 2. That is written actually. For that reason we are following this thing. Okay, so next is like this. See this quantity. If you are still now confused, again I'm showing this thing. See, if a digit is like this, 1.00 into 10 to the power 10 to the power 2, so this is 3 significant figures. Okay, we cannot change it, that's the thing. Okay, let's get to the next point. So counting the numbers of object, for example 2 balls or 20 eggs, have infinite significant figures, as these are exact numbers and can be represented by writing infinite number of zeros after decimal, or decimal that is 2 equals to 2.00. So these are the things. So, suppose I will consider one apple. Okay, I'm giving one example. This is I'm considering one example, that is one apple. Okay, so there is a particular thing, but see, like 2 balls, 1 apple, 20 eggs. Here it is given these examples. Okay, I'm taking one apple. So one apple, why it is infinite? The significant here is infinite. Why it is infinite? This is because, see, it is infinite because when we are taking this apple, it can be like this. See, 1.000, and it can continue. So for that reason it is infinite. Okay, got it? I hope you understood it, everything, I think. Okay, next I'm going further. In numbers written in scientific notation, all digits are significant. Example 4.01 into 10 to the power 2 has 3 significant figures, and 8.256 into 10 to the power minus 3 has 4 significant figures. Yeah, I think you have understood everything, all the rules, because I have explained it nicely. I hope you understood. So next thing, however, one would always like the results to be precise and accurate. Precision and accuracy are often referred to while we talk about the measurement. Precision refers to the closeness of various measurements and same quantity. However, accuracy is the agreement of a particular value to the true value of the result. For example, if A takes 2 measurement and reports the results as this 1.95 gram and 1.93 gram, these values are precise as they are close to each other, but are not accurate. Another student B repeats the experiment and obtains now 1.94 gram and 2.05 gram. So the results are two measurements. These observations are neither precise nor accurate. Next one is, this can be more clearly understandable. Now see, here another. C repeats. When the third student C repeats these measurements and reports 2.01 and 1.99 gram as the result, these values are both precise and accurate. This is the thing. See, in this table, I think you can understand this, because this is actually very easy, but some students don't get this. So I hope you have understood this thing. Just go to NCERT and just see this and read once again. I'm teaching this thing, but you have to also by your own, you have to read this thing, okay, so that you can get everything. Now this is important, this I'll teach you. Okay, what is addition and subtraction of significant figures? Okay, so if I'll consider this thing, the result cannot have more digits to the right of the decimal point than either of the original numbers. These are some significant quantities are written here. Then we are going here. See, here 18.0 has only one digit after the decimal point, and the result should be reported only up to one digit after the decimal point, which is this. Okay, let me explain nicely this thing. Yeah, so there are some digits which is given 1, 2, 3, 4. Okay, so the answer, whatever that may be, I think this is this is done. The answer, oh, just a minute. Yeah. So 12 plus 18, then plus 1. Okay, that is 31, and this is obtained. It's not one. Yeah, and this is obtained. This is the addition is done, and this is obtained this value. It's yeah. So this value is obtained, but we can see that this is one which is the most, means this is the least one. Okay, so we need to get, three significant digits, because this is the most least significant numbers that we have, that is 18.0, that is 3 significant figures. This has 4 significant figures, and this has 4 significant figures, so we need to get this. Okay, so for that reason we are doing this. Okay, that's the thing. Now let's go to multiplication and division of significant figures. In these operations, the result must be reported with no more significant figures as in the measurement with the few significant figures. So 2.5 into 1.25 equals to this much. The value has been obtained. Next, what is happening? Since 2.5 has 2 significant figures, the result should not have more than 2 significant figures. That's the thing. So this one is the least one. Okay, so we need to get this much. Has 2 significant figures. The result should not have more than 2 significant figures. Thus, it is 3.1. This thing. Okay, the main difference I have not said you. Okay, just a minute, I'm telling you this thing. See, in case of multiplication, we need to get the least significant number. Okay, I'm getting this 2.5 into into 1.25 we are getting, and from here this is, which is 2 significant figures, this is 3 significant figures, so we are taking this one. But here in case of addition and subtraction, that is a little bit different thing is happening here. That is, you need to keep in your mind this thing, that what is happening here is that we are taking that what is after the decimals. Okay, here after the decimal, that is 1, here after the decimal it is 2, and here after the decimal it is 3. So this we are considering. Okay, I just forgot to say these things to you. These are the rules for addition and subtraction. So we are taking least number, that is this one thing. Okay, got it? Thank you. Next, let's go to this. Yeah, multiplication. Since 2.5 has 2 significant figures, the result should not have more than 2 significant figures. Thus it is, yeah, we knew it. What happened? Next, while limiting the result to the required number of significant figures as done in the above mathematical operation, one has to keep in mind the following points for rounding off the error numbers. Okay, so if the rightmost digit to be removed is more than 5, the preceding number is increased by 1. For example, 1.386, we have to remove 6. Okay, see, again I will explain you this thing, what is happening here. See, while limiting the result to the required number of significant in this thing which you are doing here, like see, 3125, and the required is 2 significant figures, so we have to reduce it to 2 significant figures. That's the thing. So we'll read the rules how to do it. Okay, so we cannot do it like that only simple. No, it's not like that. It's not so simple like that. So we have to, there is some rules which we need to follow to do like this. So if the rightmost digit to be removed is more than 5, first we need to consider this thing, that suppose this is 5, whether it is more than 5 or it is less than 5. Okay, that thing we need to consider. Okay, let me explain you nicely. See, suppose this example is given, is increased. Here what is happening? Here if the preceding, see, first thing, example is 1.386. If we have to remove 6, then we have to round it to 1.39. Why it is like this? Because it is increased than 5. Okay, so as we know, so this thing first we need to keep in our mind that 1.386, we have to reduce it to 3 significant figures. Okay, we have to reduce it to 3 significant figures. So what we need to do is that the rule which says it to how to remove it, it is that if it is more than 5, the preceding number is increased by 1. If this number which we need to reduce, that is more than 5, yes, it is more than 5, so we need to reduce, we need to add plus 1 here. Okay, we need to add here plus 1. So what the final will be? 1.39. That's it. That's the final answer. Okay, this is the thing. Next, for example, 1.386. So if we have to remove 6, we have to round it to 1.39. Okay, that which we did now. Next, if the rightmost digit to be removed is less than 5, okay, so if it is less than 5, then what will happen? The preceding number is not changed. Okay, so for example, see, we're taking this example 4.334. If 4 is to be removed, I mean if it is to be done to 3 significant numbers, from 4 significance to 3 significant numbers, then if and we know this 4 is less than 5, so we there is no need to change anything, it is just as it is. Another example I am giving to you, if one number is 5.33, okay, this will be the same as that. Okay, another number I am taking, yeah, okay, 2 point, yeah, 2.12. Okay, this number I am taking, and I have to reduce it to 2 significant figures. So what I'll do, so this number which I have to reduce, so I need to remove this number, that's the thing, the first step. So what I have to do is that I have to remove this number, and I have to see that whether it is more than 5 or it is less than 5. So we know that 2 is less than 5. So what will happen now? There will be no change, it will just as it is. Okay, that's it. This is the answer. Okay, actually, why this is important, why I am explaining this again and again, because it is coming in exam every time. These type of questions used to come that reduce it to 2 significant figures. This is like a compulsory question because it comes every time. Okay, so just remember this thing. If it is not coming in chemistry, it can come in the physics. Okay, physics part also. So for that reason I am explaining it very nicely, and when I'll teach you units and measurement, the next video is that. So I will not teach this much, okay, because I have explained in this video. Next, if the rightmost digit to be removed, so I did this. Okay, yeah, another is there. If the rightmost digit to be removed is 5, then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. So this thing, yeah, this is the main point. I think you have got that doubt. Okay, we understood if it is greater than or it is less than, we understood, but what will happen if the number is 5 itself? Okay, yeah, so I am here to get your doubt done. So there are two things, sorry, yeah, again, yeah, so two things are possible here. If it is 5, see, two types of possible, see, it is written here, just I'm reading it carefully, then I'll explain you nicely. See, what is happening is that if the rightmost digit is to be removed, so here it is written that then the preceding number is not changed if it is an even number, but it is increased by 1 if it is an odd number. That's the difference. Okay, what's the difference? Again I will show you. Yes, so if it is 5, then 5, suppose one example I'm taking. Okay, let me do it like 5.68, sorry, yeah, 65. So first what I need to do is that I need to check that its preceding number is this number. I need to remove this number, I need to make it to 2 significant figures. So I need to remove this 5, and it is a 5. Okay, so what I'll do, I'll go to its preceding number, and then I'll check that whether it is even or it is odd. Okay, even or odd. So even, if it is even, yeah, and I know that 6 is an even number. So what will happen now? I'll just keep it as it is, 5.6. But I hope you have understood. This is so much messy, I know. Okay, next. And if it is a odd number, now let's go to odd number. Suppose I'm taking this digit only. Yeah, I'm not getting an example, I'm taking this one only. So 6.35 I'm taking. So what will happen? I will do it to 6.4, because I have to reduce this to two significant figures, and I have seen that this 3 is a odd number. So odd, when will happen, then I will have to do plus 1. So I did plus 1, and it is 6.4. I think this is only written here. Yeah, see, this is 6.4 as the result. Okay, I got it. Next, however, if 6.25 is to be rounded off, it is rounded off to 6.2. Here also another example is taken here, and everything is clear. Okay, I hope everything is clear, because see, I have explained nicely, I think. Okay, next, dimensional analysis. Okay, dimensional analysis. Often while calculating, there is a need to convert units from one system to the other. The methods used to accomplish this is called factor label method, or unit factor method, or dimensional analysis. But this dimensional analysis is different from what there in units and measurement, because chemistry is different from physics for that reason. Next example, a piece of metal is 3 inch. It means a little bit different. We have a lot of things there, but here a little bit of little bit is written here. Okay. Next, a piece of metal is 3 inch, represented by inch. Okay, this is, so what inch? So it is telling that inch, and what is its length in centimeter, that we need to get here. So this example, so let's do this example. Actually examples are, see, this is the solution. So we know that, let me show you again. Yeah, so that one, it is telling that 1 inch is equal to 2.54 centimeters. Okay, so what there was written, 3 inch. So just directly 3 into 2.54, do like this, and you will get your answer. That's it. Okay, but here there is a lot of explanation is written. So 1 by 2.44. So I don't think you need these explanations, because you're doing MCQ types of question, so these are not needed there. Okay, for that reason. So see, here it is given 3 into, this is the final. See, here this came 3 into 2.54 centimeters, and the answer is 7.62 centimeters. That's it. Okay, next, next the second example, also same thing. I don't think I need to explain this thing, because this is 2 liter is converted into meter cube, and here it has explained nicely. Okay, so I don't want to confuse you, for the reason I'm not explaining this thing. And this is also same thing, how many seconds are there in 2 days. See how it is given here. We know 1 day equals to 24 hour. So we know, and see, 1 hour equals to 60 minutes, then 1 minute equals to 60 seconds. Like that it has converted like this. See, like this it has converted into 2 day, into like this. So into 24 into 60 into 60. So we got this answer. That's it. Okay, next we'll go to the laws. These are, we came, finally we are in the most important part now, okay, of this chapter. And this is also a little bit less important, but the most important will be after a few minutes. Just stay now. Okay, see, laws of chemical combinations. The combination of elements to form compounds is governed by the following 5 basic laws. So these are the basic laws. Okay, the first law is law of conservation of mass. See, You just need to remember all these things because these are really important. This law was put, this date you need to remember that it is 1789. This law was put forth by Antoine Lavoisier. He in 1789 he performed careful experimental studies for combustion reactions and reached to the conclusion that in all physical and chemical changes there is no net change in the mass during the process. Hence, he reached to the conclusion that matter can neither be created nor destroyed. This is called law of conservation of mass. So, exact law is written here that matter can neither be created nor destroyed. This is called law of conservation of mass. So, question can come, who has given this law? So, it is Antoine Lavoisier. And when he gave this law, it is 1789. I hope I have said the correct thing. Yeah, 1789. So next, this law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and carefully planned experiments performed by Lavoisier. Okay, that's it. So you need to read these things because these are important things. Okay, next, law of definite proportion. So this now this law, who gave this law? This law was given by a French chemist, Joseph Proust. He stated that a given compound always contains exactly the same portion of elements by weight. Now Proust worked with two samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of elements present in it. So here the table is. So what is mentioned in this table is that see, percentage of copper, percentage of carbon, percentage of oxygen. Okay. So natural sample when he took, it came the same with the synthetic sample which is same to that. Okay, these two are equal. So what he understood by this, what we understood from this is that thus he concluded, he also understood this thing, that he concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion of by mass. Okay, so this is the thing. The validity of this law has been confirmed by various experiments. It is sometimes also referred to as law of definite composition. Okay, this thing. Okay, this also we understood in the pure substances, that we had a pure mixture and pure two were there. From that we got that pure has this thing. Okay, this is the thing. So so they are same, and what his law explained is that the source may be anything, but if but the percentage are same in every case. Okay, that's the thing. Next, law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. This thing. So what, again, let me again explain to you what is this. This law was proposed by Dalton. We know this, that this law was proposed by Dalton in 1803, that law of multiple proportions. So he told that if two elements can combine to form more than one compound, if two elements, okay, any two elements, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. That's the thing. Now for for example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Okay, this thing. See, this, when hydrogen and oxygen combines, it can form hydrogen peroxide or water. But here the masses of oxygen, that is 16 gram and 32 gram, which combined with a fixed mass of hydrogen 2 gram, bear a simple ratio, that is 16 is to 32 or 1 is to 2. That he tried to explain. Okay, I hope you got this. Then Gay-Lussac's law of gaseous volumes. Now let's read this gaseous volumes. This law was given by Gay-Lussac in 1808. Okay, this is very important, that who gave this law and when he gave. So that is 1808 by Gay-Lussac. He observed that when gases combine or are produced in a chemical reaction, they do so in a volume, or in a simple ratio by volume, provided all gases are at the same temperature and pressure. I don't think you have understood this. Again, I will explain you. See what is written here is that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Okay, so let me take example, then you can understand nicely. See here. So he told that thus 100 ml of hydrogen combined with 50 ml of oxygen to give 100 ml of water vapor. Okay, that's the thing. So when two gases combine, they give in a simple ratio by volume, they give this ratio. Okay, this 100 ml they will give. Thus the volumes of hydrogen and oxygen which combine, that is 100 ml and 50 ml, bear a simple ratio of 2:1. So this law is all about gases. Okay, this ratio, which is law of definite composition, this is also similar to this but not the same. This is all about the gases, this law. Okay, next, thus the volumes of then Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportions by volume. Law of definite proportions stated earlier was with respect to mass. Okay, this is the law of definite proportion. Okay, yeah, see the Gay-Lussac's discovery of integer ratio in volume relationship is actually the law of definite proportion by volume. The law of definite proportion stated earlier was with respect to mass. This one, it's not come. Yeah, where I am? Yeah, here this thing. So definite proportion. So this law is similar to this, but this is about volume and gases. Okay, this thing. Next, the Gay-Lussac's law was explained properly by the work of Avogadro in 1811. Then let's go to the Avogadro's law. In 1811, Avogadro proposed that equal volume of all gases at the same temperature and pressure should contain equal number of molecules. Okay, Avogadro made a distinction between atoms and molecules which is quite understandable in present times. If we consider again the reaction of hydrogen and oxygen to produce water, we see that 2 volumes of hydrogen combined with 1 volume of oxygen to give 2 volumes of water without leaving any unreacted oxygen. Okay, so let me explain this law nicely. Yeah, so Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Okay, so equal number of all gases, so equal volumes of all gases at the same temperature, so this is talking about the volumes, pressure should contain equal number of molecules. So this is equal number of, it's not working, yeah. So molecules, equal number of molecules. Okay, next, which is quite understandable. We understood this, yeah. Note that in figure 1.9 page 16, each box contains equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules to be polyatomic. If the hydrogen and oxygen were considered as diatomic, as recognized now. So hydrogen and oxygen, this point you need to understand that if question comes what is diatomic, then you need to write that it is this hydrogen and oxygen are known as diatomic. Okay, then above results are easily understandable. However, Dalton and others believed that at that time that atoms, oh, atoms same kind cannot combine, and molecules of oxygen or hydrogen containing two atoms did not exist. So Avogadro's proposal was published in the French journal de Physique. In spite of being correct, it did not gain much support. So after 50 years, it in 1860, the first international conference on chemistry was held in Karlsruhe, uh, in Germany, to resolve various ideas. At the meeting, Stanislaw Cannizzaro presented a sketch of a course of chemical philosophy which emphasized on the importance of Avogadro's work. So this only the story which happened there. Then Dalton's atomic theory. Then this is actually examiner's favorite theory because they love to ask from this part. Okay, we need to get into that. That is what Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher, 460 to 370 BC. It again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Matter consists of, these all are important, okay? Let me tick this. Yeah. So matter consists of indivisible atoms. Then all atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. Compounds are formed when atoms of different elements combined in a fixed ratio. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. That's the thing. So we cannot destroy any atom. We can neither create or can destroy them. We can only form. We can change their properties by forming any other atom or any other molecules with and their property can be changed. Okay, that's the thing. Next we have what? Yeah, Dalton's theory could explain the laws of chemical combinations. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. Okay, this we understood. Next, atomic and molecular masses. After having some idea, this is the most important part which I talked about before. So these part and these one also. Now I'll do some MCQs and everything to explain you all about these. Okay, the questions also I'll make you practice. Formula mass and every type of question which come in the examination, I will just make you friend with them, so that you will not live anything. Okay. So first is atomic and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. Okay, we need to understand this thing. First thing is that atomic mass. The atomic mass or the mass of an atom is actually very very small, because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. This thing you need to remember, this thing, that we have this device, that spectrometry, mass spectrometry. Okay, for determining the atomic, what this is used for, this is used for atomic masses, to determine the atomic masses. This is really very important, because it can come as MCQs. So they can ask you that what is the mass spectrometry used for, or it could be asked that atomic masses are measured accurately using which instrument. So you can tell this thing, that it is mass spectrometry. Okay, that's it. Next, but in the 19th century, scientists could determine the mass of one atom relative to another by experimental means. As has been mentioned earlier, hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements that were assigned masses relative to it. However, the present system of atomic masses is based on carbon 12 as the standard, as and has been agreed upon in 1961. Here carbon 12 is one of the isotope of carbon and can be represented as 12 C12. Okay, so in this system C12 is assigned a mass of exactly 12 atomic mass unit, which is AMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal. Okay, one thing I'll show you here. I went through two important points are there which you need to okay, let me show you in this note part. Okay, see, so first thing is that you need to write this in your copies wherever you want. Modern scale. So what is the modern scale? Modern scale is 12C. Okay, 12C is the modern scale. Okay, this is the modern scale. First thing you need to remember this thing. Next, what is 1 AMU? That will also I'll show you. So this for what this modern scale is used for? This is used for to measure. This is so, yeah, oh my god, it's not showing also. Yeah, again I'm writing. What happened? Yeah, so to measure the atomic mass. Okay, write this down, the atomic mass. Okay, so then this is the first thing which we knew. Next is so how it is measured. Sorry, 1 AMU. Yeah, I'll show this thing, that 1 AMU or atomic mass unit is equal to 1 by 12th part of, just write this thing, 1 by 12th part of carbon 12 atom. Okay, of carbon 12 atom. So 1 AMU is considered as to be this. Let me write it again if you have not seen clearly. What is 1 AMU? I am writing here. The heading is 1 AMU. What is this? This is equal to 1 by 12th part of, okay, part of carbon 12 atom. Got it? Carbon 12 atom. Fine. Yeah. So I hope you have understood these. Next is here carbon 12 is one of the isotopes. So and we know that carbon 12 is one of the isotopes of carbon and can be represented as this thing. Okay, we got it. Next, one atomic mass unit is defined as a mass exactly equal to, I think which I have explained, this is only written here, exactly equal to 1/12 of the mass of one carbon 12 atom, and AMU equal to 1 AMU equal to this value. Also remember this value, 1 AMU equal to 1.66056 into 10 to the power minus 24 gram. Okay, then mass of an atom of hydrogen equal to this is the mass of an atom of hydrogen. Okay, this is also again one standard, because when we measure anything else we just do like this. Okay, thus in terms of AMU, the mass of hydrogen atom equals to this, see, 1.6736 this mass of an atom divided by 1 AMU. This happened and we got this value. Okay, next, similarly the mass of oxygen 16 atom would be 15.995 AMU. At present AMU has been replaced by U, which is known as unified mass. So now wherever you write these things you can use U. Okay, next, when we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. So what is average atomic mass? Let's see. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance, percent occurrence, the average atomic mass of that element can be computed. For example, carbon has the following 3 isotopes with relative abundances and masses as shown against each of them from above data. The average atomic mass of carbon will come out to be, see here we are doing this thing, see isotopes are there. So if you have not understood this thing, again I will be explaining this thing. See what is this. So isotopes, so see carbon has 3 isotopes, so which is carbon 12, carbon 13 and carbon 14. So we have 3, according to that we have 3 atomic masses also, AMUs. So 12, 13.00335 and another is 14.00317. That's it. So what happens here is that we need to get the average of this. So how we can get the average? We get the average from this 0.9982892. Okay, let me show you what this is. See, into 12U plus 0.01108 into this 13U plus getting this, and then we are getting the value which is 12.011U, and we are taking its approximate also. Wherever we are asking any question about what is the atomic mass of carbon, what we are writing? We are writing 12. That's it. We are not writing it 12.011U. That's needed in the higher classes, but not now. Okay. If there is given that the mass is this, then you have to mention that thing. Suppose there is a question, and but if there is nothing is given like that, suppose it's just written CO2 and find its molecular mass or something like that is given the question, then you can use this 12 plus 2 it's not, yeah, 2 into 16, okay, then you can get this answer. But if there has been written that the atomic mass of carbon is 12.011 u, then you have to take this quantity, okay. I think you have understood this thing. Next, similarly, average atomic masses for other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic mass, okay. This is the thing. Next, molecular mass. So now I was talking about that only. Molecular mass is the sum of atomic masses of the elements present in a molecule. That's the thing. It is obtained by multiplying the atomic mass of each element by the number of its atom and adding them together. For example, molecular mass of methane. So let's do this. Suppose molecular mass of CH4. So what happens here? We are taking carbon 12 plus we have 4. So 4 into this 1. Okay, and this is what? This is 1 into 12. It is just 1. And here it has 4. So it is 4 into 1. 1 is the atomic mass of hydrogen. That's it. And we get the value. Value is 16. So we write it 16, not 16.043. If it is mentioned in the options or something like that, then you have to take that thing. But usually we do this. Okay. Next. Similarly, molecular mass of water. See, molecular mass, similarly it is given. See, 2 into 1. We are taking here, they are taking hydrogen as 1.008 u. So it's not needed, we can also take like that only. 1. So plus 16. It's 18. Okay. Next, formula mass. So what is formula mass? Some substances such as sodium chloride do not contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are arranged in three-dimensional structure as it is shown. See, it may be noted that in sodium chloride, one Na plus ion is surrounded by 6 chlorine ion and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state. Sodium chloride does not exist as a single entity. So I hope you have understood this line because it's so simple. Next, thus the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. That's it. Then we need to add it like this, which is 58.5 U. Okay. Next, mole concept and molar mass. So what I'll do is that molar these things I will just first explain you, then I will read these lines, okay, because it's not so simple. Okay, first I'm teaching you the introducing lines. So that is what first is atoms and molecules are extremely small in size and their numbers in even a small amount of any substance is really very large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen of 12 items, like that score for 20 items, then gross for 144 items. We use the idea of mole to count entities at the microscopic level. So that is atoms, molecules, particles, electrons, ions, etc. In SI system, mole or symbol this mole was introduced as 7th base quantity for the amount of a substance. So here there is a what is the meaning of mole, that is written, the definition. 1 mole is the amount of a substance that contains as many particles or entities as there are atoms in exactly 12 gram or 0. Yeah. So or 0.012 kg of the 12C isotope. I think you have not understood anything. Now I will show you what it exactly is. Okay. See, let me clear this first. Done. Next, so what is 1 mole? So first thing is that 1 mole is what? So 1 mole has, first thing is that it is gram atomic weight or gram molecular weight. Okay, the first point is that it is gram atomic weight or it is okay, gram molecular weight. There is not so space, for that I am writing like this. I think you just write with me so that you can understand this. Gram atomic weight or gram molecular weight. Okay, atoms, number of atoms or molecules, this is molecules, equals to 6.023 into 10 to the power, okay, 10 to the power 23. Okay, so this is the value of number of atom or mole or molecules. Okay, so this thing, why I am explaining, I'll just after few minutes you can understand this. Oh. Done. Next, another point also there. Another point is STP. Okay, its STP is what? STP means standard temperature or pressure. Okay, it's standard temperature or pressure or volume also you can tell it. So it is what? It is 22.4 liter. That's it. Okay, I hope you have understood this thing. If you have not understood it, then this moment you can understand this. Okay, we got 3 points. What it exactly represent? You need to write these in your copy. That number of atoms or molecules equals to 6.023 into 10 to the power 23. STP is 22.4 liters. And this is what? Gram weight or gram atomic weight or gram molecular weight. 1 mole equals to that only. Okay, now I'll explain you what exactly it is. Let me first erase this down. Yeah, done. So suppose there is a question which asks a number of atoms or molecules. So what is the number of moles, or what is the number of molecules, or what is the number of volume? So these questions we can handle now. So I will show you how to do this. So 1 mole of suppose number of atoms or molecules equals to Avogadro number. That is actually number of atoms or molecules is the Avogadro's number. So I told you that Avogadro number, that is 6.023 into 10 to the power 23 molecules. That is the Avogadro number. So we got it. Now suppose this is number of moles are given. So now I can show you. Okay, let's do a question. Let's do a question so that you can know what I'm exactly talking about. Suppose this water is given. Okay, so water is given and then 1 mole of water. We are asking what is the exact what is the molecules present and what is the volume of this thing. Okay, what is the, okay, see, I'm writing here 1 mole of water, H2O. Okay, so what is this? So we need to measure its volume and measure its molecules, okay, number of molecules. So first thing, we need to know this thing that water, we know, as we know, it is 18 grams or 18 units also. So 18 units or 18 grams means it is the molecular mass of water. So 18 gram of this water contains 6.023 into 10 to the power 23 molecules. Okay, I hope you have understood this thing. These questions only will come. Oh yeah. Okay, then next, what is the volume? And this 18 gram or the 18 units contain 22.4 liters. That is the volume. Okay, that's it. I hope you have understood nicely this part. So now I will explain again. So now I'll give you formulas how to do this, then we'll do some questions. So the first formula is number of moles. So how we can just calculate number of moles? So number of moles is what? So to calculate this, we need to write the, suppose a given one mass is given or a weight is given, and it is written that find the number of moles of any, suppose H2O, suppose water, it is given and it has written that find the number of moles. So what you need to do? You need to do the given weight, okay, you need to write the given weight divided by molecular weight, or you can tell it gram molecular weight. Okay, that's it. So it is in gram, for that the standard is in gram, for that reason I have written here gram molecular weight. This is the way you can find this. Yeah. Next formula is number of molecules. Okay, so number of molecules. So to find number of molecules, what do you need to do? You need to write, so gram weight or the given weight, this is given weight divided by this gram molecular weight, okay, into, this is multiplied by the Avogadro number, that is 6.023 into 10 to the power 23. Okay, here is no space, for that I am writing like this. So 6.023 into 10 to the power 23, that's it. Okay, I hope you are understanding, because it's not so difficult. And when we'll do questions, you can understand it nicely. Okay, next is volume. We can also calculate volume using this. What is that? Volume equals to gram or given weight, this is given weight divided by gram molecular weight, same thing, into 22.4. that's it. This is the way to calculate volume. Okay, I hope you have understood everything. Now let's do some questions. Okay, when you'll do some questions, you can understand everything. So questions are like this. First question is, suppose one question I'm taking, these are actually, I will do most of the previous year questions of NEET, so that we have chances of coming these questions again and again, and the value may change, but the question pattern you can understand, that these type of question, the trend of question you can understand. Okay, So the first question I'm doing is that just nicely listen to this question. I'm just writing the main points of this questions. That is, for 4.4 gram of CO2 or carbon dioxide, find number of moles, molecules and volume. So this one question can clear all your doubts, that yeah I can solve questions. You will feel the nice good, you'll feel good really. See, the first thing I'm writing here, 4.4 gram of CO2, okay, of CO2, this is there. We need to find its number of moles, we need to find the number of molecules, and we need to find volume of this question. Okay, such easy question. Now I'll show you. If you are finding it difficult, then also you will, after solving this, you can know that yeah, it's a very easy question. Okay, let me erase this. Not saying. So 4.4 gram, this much is important, gram of CO2, that's it. First let me find the gram molecular weight of this. So carbon equals to 12, then oxygen, there is 2 into 16, okay, so it is 12 plus 32, that is 44, okay, this much. So we got this much, that what it is exactly, the molecular weight is now set. Next we'll move further to this, that solve number of moles. Okay, number of moles is what, given weight by molecular weight, so simple. So let's write 4.4 divided by 44, this is I'm finding moles, okay, moles. So 4.4, so what will be the answer, this will be 0.1 m, that's it. So simple, have you found it, so simple it's. Okay, we got one answer. Second answer, that is molecules. So molecules, what we need to do here, here is 0.1, so I am doing it like this, 1 by 10. Already you know that we have to do it like this, that given mass by molar mass. So I am doing the same thing here, this is the answer, 0.1, so I am writing like this, 1 by 10 into 6.023 into 10 to the power 23. So for this reason I'll only did this. So it's very simple, we don't need to touch this one, just let's do like this. What happened, oh sorry, yeah, so we need to do like this, that's 6.023 into 10 to the power 22, that's it, answer came. Great. Next we need to get this answer. I think you got the answer, so I am erasing this. Okay. Next one is this volume. Volume also similar way I am doing this. 1 by, so this is 22. We know the formula that we need to multiply 22 into 22.4 divided by 10. I am doing because I've got this answer, right? 1 by 10. So this is the same thing. What we can do here, that this will be 2.24, that's it, and we got all the answers. So simple questions. Okay, have we got it? Okay, next, this much I hope you have understood this, so I'll erase this. Okay, done. So all these more types question is done now, the 3 which I explained now. So I think we are done with this. Now let's go back to the NCERT and see what else is there. Yeah, the same thing which I explained here, Avogadro constant and these are things, these all are only there. here one important point is written. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the constituent entities. The mass of 1 mole of a substance in grams is called its molar mass. Okay, so molar mass. And molar mass is also the same thing only the difference is that we need to write like this, gram per mole. That's the molar mass. Same to molecular mass. Okay, like see, the difference between, I'll show you today. Okay, pen, yeah, come. So the difference between the two are the major difference, yeah, that's the major difference, that is molar mass. Okay, first let me tell you this molecular mass. Molecular mass here I am writing, and molar mass I'll do here. Okay, so the major difference which it has is that it when we write this, I'm getting it of water. Okay, so water, the difference is that we know it is 2 into atomic mass plus this, like this, the value is same. This is 18, this is also 18. Only the difference is that it is this one, this molar mass is this one, yeah, gram per mole this is, and here we write u. This is the only difference that we have in the units. Okay, and nothing more problem. Just don't do like this, just similar to this one. See, here also it is written molar mass is in grams is numerically equal to atomic or molecular or formula mass in u. That's it. Next, percentage composition. Okay, before this there are some more terms which is not mentioned in Ncert, but it is very important. You need to know these things, so I'll explain you here. Okay, in the notes part. So the first point is that we need to first get the charge and all these type of, one question is there. Okay, let me solve one question and show you how, which type of question actually comes. So find charge, so the question I'm reading, find charge and mass of 1 mole of electron. Okay, so what is 1 mole of electron? This thing we need to get. So 1, and this can be of proton also. So 1 mole of electron. Charge of electron we know. What? How much charge of electron is? Charge of electron is 1.6 into 10 to the power minus 19 coulomb. That's it. Not yeah, minus also we can write here, but not needed. Next, 1 mole of electron. So 1, here there is no space. Then we'll mention here 1 mole of electron equals to 1.6 into 10 to the power minus 19 coulomb into 6.0, which is the Avogadro number, 6.023 into 10 to the power 23. Okay, we got it. And what will get the answer? The answer will be very simple. This will be 6 into 1.6. This will be, we are taking the see, this will be 96368 coulomb. That's it, 96368 coulomb. Okay, and exactly this is, see again I'm another thing also there. We approximately take it as 96500 coulombs, and we this is actually equal to 1 Faraday. So, and this whole thing, this 1 mole of electron and these all things is known as specific charge of electron. Okay, this is known as specific charge of electron. Okay, that's it. I hope you understand. Please note this down. Okay. And another thing I'll mention here. Okay, let's go to another question. This is done. Another question is, let's get mass of 1 mole of electron. Okay, and this mass, this procedure, this of getting mass of 1 mole of electron is known as rest mass of electron. So I'm getting this. So mass, we know mass of electron. So see this thing, charge of electron, 1 mole of electron is a charge which we got, charge of 1 mole of electron. That is also similar in case of protons, but this mass case is different because we have different mass of proton and different mass of electron. Okay, for the reason it is not the same. So we know mass of electron is 9.1 into, it's, yeah, oh my god, again. So mass is equal to 9.1 into 10 to the power minus 28 in grams. I am writing, okay, minus 28 grams. 9.1 into 10 to the power minus 28 grams. Then we need to get the mole. So mass of 1 mole, need to write here, mass of 1 mole of electron is what, how much? This will be 9.1 into 10 to the power minus 28 into 6.023 into 10 to the power 23, and the answer is 54 into 10 to the power minus 5 grams. 5 this is, okay, 10 to the power minus 5 grams. So let's convert it into, if we are converting it into mg, then it will be how much? It will be, just do like this, it will be 554 into 10 to the power minus 2. So if it is minus 2, then I can also write it as 0.54 mg. That's it. Okay, and this whole thing is known as, I'll show you here, this whole thing is known as rest mass of electron. Rest mass of electron. That's it. Okay, I think you have understood nicely. Next, let's do another question. Another question is, find weight of one atom of hydrogen. Okay, so let's do this. Weight of, this type of question also come in examination. Weight of one atom of hydrogen. What is that? So we know weight equals to, this is actually, this looks very difficult, but actually it is very simple. The question is this: weight of one atom of hydrogen, and the answer is very simple. Just follow me. It is that weight of 6.023 into 10 to the power 23 atoms equals to 1. I think you have got it, because this is the exact atoms which hydrogen contains for 1. Then weight of, now we will consider this thing, that weight of one atom is how much? It is 1 by 6.023. The same thing. I think you know this thing. Actually, I have no space here. Oh, let me write here. This is equal to 1 by 6.023 into 10 to the power 23. This is equal to, here 23 will go up and it will become into 10 to the power minus 23. Okay, and when we'll divide 1 divided by 6, it will be approximately come as 0.167. okay, and this is the value. Okay, and we can also do like this, that 1 point, okay, let me do like this first, and we can also write this as 1.67 into 10 to the power minus 24. That's it. Got it? Okay, now let's go to the next question. As much question will solve, we will be more confident and everything will get easier. Okay, for the reason only I am solving questions. So will I solve or not solve? Okay, I'm solving it. Now we got atom. Now let's go to molecules. Okay, now let's get the weight of one molecule of hydrogen. Okay, sorry, not hydrogen, it's water, of H2O. Okay, because it's a molecule. Hydrogen is not a molecule. We have solved it also. I looked at the previous question. Okay, so this is what? This is weight of 1 mole of H2O. Weight of 1 mole of H2O equals to, okay, tell me the molecular mass of H2O. What is that? That is 18. Yes, it's correct. It's 18. So we got this much. Then now we'll get, so weight of 6.022. So now 6.022 into 3 into 10 to the power 23 equals to 18. So here changes will happen when 1 will be written here, 1 molecule, right? So this is 6.023 into 10 to the power 23 molecules, weight will be 18. So now 18 divided by 6.023 into 10 to the power 23. So the answer will become so what will the answer? Yeah, the first thing is that 23 will go upwards and it will become minus 23. And then what will happen? 18 divided by 6. So it is, I think, approximately it is into 2, or sorry, it's into 3. So it will be 3 into 10 to the power minus 23. Okay, fine. I hope you have understood this thing. So the answer we got. So next let's get another concept. So another concept is what? Calculation of number of electron, proton and neutron. This thing we'll get now. So electron, proton and neutron are three subatomic particles which are in an atom. Okay, so the first thing I'm writing here, electron, proton and neutron. So I am denoting A as atomic weight and electron as Z. This is actually the denotation only. Suppose I am writing an oxygen, here I am denoting 8 and here I am writing 16. It means what? 8 is this Z, which is electron, and 16 means A, which is atomic weight. Now I'll show you how to find the other things. Like the first is proton. Proton is what? Proton is equal to electron. Electron which was equal to Z. That's it. Next, the atomic number. Atomic number equals to proton plus neutron. And another thing is that how to get neutron. Neutron equal to A minus Z, which is atomic mass or atomic weight minus this is electron, or you can also do that atomic weight minus protons. Okay, same thing. So you have got it. These are the things, and these are important because you need to know these things. Okay. Next is let's solve a question if you want. If weight is given, then number of electron, proton or neutron is in another level, it is there. Okay, if weight is given, if in a question, what I'm telling, just understand it nicely. If in a question there is given that this much weight of this, of H2O or anything is given, is this, and then find the number of electron or proton or neutron, whatever it is given, then how can we find it? Okay, we can find it by this formula. It is number of this, I am here denoting this, electron, proton or neutron equals to the given weight, okay, divided by gram molecular weight, gram molecular, I don't have space, so how I'll write this? Okay, let me just minimize it a little bit. So you have understood this. This is gram molecular weight. Then into, we'll do it by number of electron, proton or neutron, whatever it is given. For that I am writing like this: number of electron, proton, neutron into the last thing, that is, this is electron, proton and neutron in one molecule you need to write. Okay, one molecule, in one molecule, and then into 6.023 into 10 to the power 23. That's it. Okay, I hope you have understood this thing also. Okay, we'll do now some examples, you will understand nicely. See here, I have minimized it. Now you can look at the formula nicely. See, what is this? Number of electron, proton or neutron equals to given weight by gram molecular weight into number of electron, proton or neutron in one molecule into 6.023 into 10 to the power 23. That's it. Now let's solve one example, solve one question, whatever. This is an example. Now I am solving it. Find the number of electron in 1.6 gram of CH4 or methane. Okay, so number of electron, electron in 1.6 gram of CH4. So let's solve this question. Great. So this question is like this. Let's solve it. So what is what the formula we got? So we are solving here number of electron. So we have to write that 1.6. This is that, and then we have to find the molecular mass. What is the molecular mass of this? So carbon will be 12 plus H4, which is 1 into 4, that is 16. Okay, so it will be 16 into what will be this? The electron in it is telling that of this in one molecule. We need to find out the number of electron in one molecule. So what will be this? Carbon will be 6 plus 4 hydrogen atoms, so it will be 10. So that's it. It will be 10 into 6.022 this thing, This is 6.023 into 10 to the power 23. That's the formula. Now let's solve it. So first thing is that 1.6, so this will be, first this will be 10, 1 by 10, and then 10 will get cancelled, and this will be the answer. Okay, now I'll show you what the answer is. The answer equals to the Avogadro number, that is 6.023 into 10 to the power 23. Okay, that's it. Now let's solve another question, and that is the last question. Move towards NCERT text. Another question is about neutrons, and I need to tell you something about neutrons. So for that reason I want to solve this question. Okay, so the question is that how many neutrons are there in in 49 gram of H2SO4 or sulfuric acid. H2SO4, there is no space. Oh, so this is our question. I'll write it nicely. Wait. 49 gram of H2SO4. Okay, this is the question. Now let's solve it. So to solve it, first thing we need to get that what is the number of neutrons. So atomic means number of neutrons are, see, first thing we need to I need to tell you that, as we know that it is atomic mass minus this electrons or protons also it can be. So we know that hydrogen atom has 1 as its atomic mass, and it is 1 in as it is 1 electron. So for that reason it is 0. So we have to consider this 0. Let me again do this thing. Then I'll do something. Yeah, here. So H2 if I'll consider, then S I will consider, and O4 I will consider. Okay. So the first thing, if we'll consider the number of neutrons, that will be here this will be 0. Here this will be just think it. This is 16. This is 32. 32. Here this is 8 and this is 16. So this will be 16 and this will be 8. That's it. So then 8 into 4 this will be, because it is 8 into 4. 4 atoms are there. So 8 into 4. So it will be how much? The quantity will be, yeah, this is 16 and this is 32. When we will add it, it will be 48. Okay. I can do like this also. Okay. And we know that it's calculate its molecular mass. Molecular mass will be hydrogen will be 1 into 2. 1 into 2. Then I'll erase these things. This is 16 and 32. So this plus 32. Then this is plus, here this is 16 into 4. That's it. So it will be 2 plus 32 plus 16 into 4, which is 64, and the answer will be 98. Okay, now we finally got these, that what is the molecular mass and what is the number of neutrons. Now we can easily solve this question. So what will be this? This will be it is, the given mass was 49. So 49 divided by 98 into 48. This is the number of neutrons. Then into the Avogadro number. So first let us find this thing, because I don't have space for that. I'm doing it. This 49 into 2. This will be this. Then 2, 2 2s are 4, 2 4s are 8, 24. Next we'll get this. So 24 into 6.0, 24 into 6.023 into 10 to the power 23. This is equal to 144 into 10 to the power 23. That's it. So that's it. Now let's go to the NCERT text. Okay, I'm erasing these parts. The next thing, let's go to NCERT text now. So here, what else is there? Yeah, so the percentage composition. So this is all about another thing. This is what, so far we were dealing with the number of entities present in the given sample, but many a time information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is, what is the formula? What is its formula? Yeah, the first question will ask that only. So, or what are its constituents, and then what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. Yeah, so this is the meaning. Yeah, okay. Next is in other. So this is all the text which is written. See here, this is written. The important thing is, let us understand it by taking this example of water, H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated. Mass percent of an element, mass of that element in the compound into 100 divided by molar mass of the compound. Yeah, okay, this is like mass percentage of the element, and these are only written. See here, then there is an empirical formula, then these are the limiting reagent, then here we have reactions, then see, these all are only there, and I'll teach everything. Okay, so don't worry. Okay, so let me start this. So first one is the mass percentage. Here there is what? Here there are mass percent or weight percent. Okay, this is different than this. So the first thing is, where it went? Yeah, here. So this is percentage composition, and now I'm going to explain these things clearly here. Okay, so suppose here written that hydrogen, mass of that element, suppose in water is given here, and then what is good? Okay, let me do these examples. I'll do this in a fresh page, because these are all about that only. Okay, let me write this. Okay, so the first question is something else which I'm doing now, that is find percent of oxygen in NaOH. Okay, so sodium hydroxide. So percentage of oxygen in NaOH. We are going to find this thing. Okay, so what's the formula? First we need to get the weight of these things. Okay, so first let me put this like this. Yeah, so we need to get the weight. So we know NaOH, the weight of NaOH is 40. Okay, so weight of NaOH is 40. and the weight of oxygen, here it is, I am putting O2, that is 16. Okay, here then what we need to do is that I'll put here that 164, this, see this thing, I'll just again I have to do like this, yes. Then what we need to do is that I need to get the percentage of oxygen. For that reason what I'll do is that I'll write here 16, so weight of oxygen divided by weight of NaOH, that is 40 into 100 here. Okay, so I'm cutting this, then 4 4s are 16, and the answer is 40. Okay, so it is 40%. So 40% of oxygen is present in NaOH. Okay, it's done. Next, let's go to another example if you're interested. I think personally that the more you do the questions, the more your concepts will get clearer. So I'm doing another question for you. So I'm doing one question of urea. Okay, this can be tricky question, means if the formula is not given, by this you can know the formula of urea also. So we need to find the percentage of nitrogen in urea. Okay, so here it is given urea. So first we need to write the formula of urea. So the formula of urea is NH2C, then this is double bond O, then NH2. This is the formula of urea. I think you must be knowing this, but still if you don't know, then it's for you. Okay, so this is the formula of urea. Now we can know that two nitrogens are there, so we need to okay, first I will find the weight of NH2. It means weight of urea first I need to get. Okay, so I'm getting the weight of urea now. So what will be the weight of urea? Okay, we know that nitrogen is 14 into, see 2 are there, so 2. Next carbon 12, 1 is present, so into 1. Then here hydrogen 4, so I'm simply writing it 4. Then oxygen 1 is there, oxygen is 1, so it is 16. Okay, that's it. Next let's completely get it, what will be the value. So 14 into 2, 28, plus 12 plus 4 plus 16. Okay, so 28 plus 12, it will be this is, see 4 plus 16. Okay, there is no space again. Oh, 1 is remaining here. Okay, fine, I have to erase this. Yeah, so here I got the mass, it is 4 plus 16 is 20, and this is 40, so it is 60. That's it. So we got the mass, we got the weight of urea. Now N2 is 2 is there, so it is 28. Okay, 14 into 2, that is 28. Now we got, now let's find it, 28 by 60 into 100. So I'm cutting this, then 6, then the answer will be this is actually decimals, so 46.66. I'm cutting everything and I got this answer. So it is, again let me write this. So the final answer 46.66%. Okay, that's it. And I followed this accuracy one, so for that I have written this 66. Okay, so this question is also done. Now the NCERT question, it is written, So I'm not doing it again, and that is the example. This example, just look once. It is very easy, like I did. Just ignore this 0 2 or something like that, this 1.008, just ignore these things, and or else it will be easy. Okay, next let's go to the empirical formula of molecular mass. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in the molecule of a compound. If the mass percent of various elements present in the compound is known, its empirical formula can be determined. So it's very easy. This is very easy thing. So molecular formula can further be obtained if the molar mass is known. The following example illustrates. See, these are the examples. So just follow these examples. The compound contains, it is given. So it's very easy. Just look at it once and it will be done. Okay. So I don't want to waste your time. So I'm just going to stoichiometry and stoichiometric calculations. The word stoichiometry is derived from two Greek words, stoichion, which means element, and metron, meaning measure. So stoichiometry thus deals with the calculation of masses, sometimes volumes also, of the reactants and the product involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or the products produced in a chemical reaction, let us study the information. What information is available from the balanced chemical equation of a given reaction. Let us consider the combustion methane. A balanced equation for this reaction is as given below. So this is all about this only, and see. Okay, one thing I forgot to show you. Okay, that is a different type of problem. Okay, let me complete this, then I will go there. That mass, that percentage one chapter, that way there. So balanced chemical equations is this, C4, yeah, C4 sorry, CH4 plus 2O2 gives us CO2 plus 2H2O. Okay, then here methane and oh yeah, let me cut this. Okay, yes. So dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products of gases, what happened? Okay, yes. Of this gas, where I was, yeah, here. Here methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction. Sorry. And this has been indicated by a letter G in the brackets next to the formula. So these are, see, G means gas and then S means, see here it is written also. Similarly in case of solids and liquids it will be like S and L. L means liquid and S means solid, like that. And where there will be aqueous solution, that would be AQ. That's it. The coefficient for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CO2 is one in such case. They represent the number of molecules and moles as well, taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 reacts with 2 moles of O2 to give 1 mole. So just read these, because if I'll read like this, you can't understand anything. So you need to read yourself. Okay. So here also they've written that mass by volume equals to density, then limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situation, one reactant is in more amount than the amount required by balanced chemical reaction. The reactant which is present in the last amount gets consumed after some time, and after that further reaction does not take place, whatever be the amount of the other reactant. So this only happens in this case. So hence the reactant which gets consumed first limits the amount of product formed and is therefore called the limiting reagent. I hope you have understood this thing, and just remember this definition because it is important and is forming stoichiometric calculations. This aspect also to be kept in mind. Reaction in solutions. Now we will read this thing. A majority of reaction in the laboratories are carried out in solutions. Therefore it is important to understand how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following ways. See, these are the ways: mass percent or weight percent, then mole fraction, molality, and some different are also there, like normality. That will also I will explain you. Okay. Next, let's get into this. Yeah, so this is where it went. Yeah, here. First one is mass percent. So before explaining this, I have another thing which I need to explain. I forgot about this. Now I'm going to do this exercise. Actually, previous thing, that is that the proportion, there were another percent of an element that time, another left. Okay, another question I'm going to do which comes in the NEET exam, so it's actually important. So for that reason I'm doing this question. So this type of question also comes in this type of exams. So let me do it, and that is so simple also. In a sample of insulin, just listen the question nicely. In a sample of insulin, 3.4% of sulfur is present. What is the molecular weight of insulin? This is the thing. Till now we have found that a percentage we were finding, and then we got the answer. Now I'm going to find that in a sample of insulin. So we understood from this question that insulin is there, and 3.4% of sulfur. So before we used to find that sulfur is this much, and the given means mass is this much, so find this. But now we are doing this type of question where we are doing this type of solution, and we need to find the molecular weight of insulin. Okay, we need to find the molecular weight. So okay, so we need to find the molecular weight. What is the molecular weight? That we need to find. So now let's get started to find this thing. Okay, so you need to use your concepts. Before this, what we used to do, we used to find this x. Suppose let's take x, the percentage I'm taking it x percent. Okay, and that was equal to how we used to find it. Suppose sulfur is given. Suppose in this question, suppose sulfur is given and then insulin is given. So we need to we were, what we were doing is that we were finding the molecular formula and molecular weight of these two, and then we used to do it into 100. So this thing we used to do. Now what is happening is that this is given. Okay, let me like So next, now the question what is it acts is that, see, now insulin is there. See, this is S, I'm writing it as S. I'll further I'll write here. Now 3.4% that is given, and insulin is now X. Now we need to find the molecular weight of insulin into, this is 100, this thing. Now let's proceed further. So to do this, what we need to do is that, see, first what I'll do is that I need to get the sulfur. What is the this, that sulfur is 32, the molecular weight of sulfur is 32. So this thing we need to write here. Now X I'm taking to this side, and then 3.4 I'm dividing it. Okay, then sulfur we know that is 32. That's it, it's done. Now it's 1000. Okay, now I have to see one new thing which I'm doing, by which a calculation will become easier. That is, oh, okay, again. Yes. Next, what we'll do in the next step, I'll write here. See, I'm taking X equal to, then here 34 into, I'm taking the decimal above, then I'm multiplying this, then here I'll do, what is that, 16, this is 16, 2 into 16, then 2 into 17, it is 34. Then the answer is straight here. The answer is, okay, I'll erase this thing because it's not visible also, and the final answer is 941. Okay, this is the answer, and 941 is the molecular weight of insulin. Okay, that's it. So if these type of question will come, can you handle this? It's really easy. Now let's get to the question, the molecular weight and all. This is completed. Now we'll do the concentration terms. So concentration terms, so first let's do molarity, or let's go to the text. Okay, so here there is mass percent. First is mass percent. So mass percent is what? Mass percent is something which is like mass of solute divided by mass of solution into 100. I think a lot of medicines there is written like 5% W by V. What does it mean? Now we have only this type of terms, like, which is percentage weight by weight. So I'll show you what it is exactly. See, when it is written something percentage weight by weight, how can we find? Okay, let me change the color, or blue I'm doing. Yeah, again. So mass, so this is weight by weight. Okay, mass percent, this is weight by weight. What it is? So it is mass of solute, it is written here, mass of solute divided by mass of solution, here it is written, into 100. Okay, so we just take the solute and the solution. Okay, one trick which I am going to say you is that wherever the question will be written that 20% mass, 20% mass, if it is written, then what will be the reason there, that it is 20 by 100. See, then it will be 20 by 100. which means 20 gram and 100 gram. 20 gram of solute is present in the 100 gram of solution. The meaning is that, and 80 gram of solvent is present. That's the meaning. Next, this example is given which will clear all the doubts. Next is mole fraction. Mole fraction is what? Mole fraction is very simple thing. It's only the number of moles of A divided by number of moles of solutions. So number of moles of A means, that means you can take solute or you can also take the solvent. So you need to get that moles of solute, number of moles of solute divided by number of moles of solution. The meaning is that. And if you don't know, let me tell this thing that how to calculate number of moles. So number of moles is very simple. This Na, I'm writing here Na, this is equal to, see, you need to divide, this is mass which is given mass by molar mass. That's it. And I have told the difference between molar mass and molecular mass. That's it. So, and it's done. Okay, so this means this given mass by molar mass. So this only applies here, and it's very easy, not so difficult, nothing else. And another and two things are there, that is, if x, we represent this as x. Okay, you need to get here that a mole fraction is represented by x. So another thing is that this is represented by x, and I'm writing here some, see, xa plus xb is always equal to 1. xa means mole fraction of solute, and xb means mole fraction of solvent. So this is always equal to 1. So if xa is given, then you can find, suppose xb is given, then you can find xa, like minus xb, like that. Okay, is it clear? I hope it's clear. Okay, next is molarity. Yeah, so molarity is very simple. It is represented by capital M. Here also it is given. Then number of moles of solute divided by volume of solution in liters. Okay, this formula I should actually write again and show you how we need to write this. So as I said, you number of moles equal to given mass by molar mass. So this thing we will follow and write here. So M is molarity, this capital M. So this is divided by mole of solute by volume of solution in liter. Okay, volume of solution in liter. This is the meaning. Then there are three. Okay, yeah. So as we know that it is given mass by molar mass, these moles, so we have another thing for it, and also the unit I'll tell you now. Okay, let me tell the unit. Unit here is, see, can you guess it, what it can be? It is moles per liter. Okay, that's the thing. Next, then here what will happen is that M equal to this given mass by mm, which is molar mass, into 1 by V in liter. This is okay. And then if it is in if this is in ml or milliliter, then what will be the formula? It will be simple, like given mass by molar mass into 1000 divided by volume in this is ml. Okay, that's it. So this is also done. Another formula also there, which is actually important and it is not given in the textbook, so we are going to deal with that. Another formula is Another formula where if molar mass is given and percentage weight percentage is given, then it is applicable. Okay, and I will do a question related do to that also. See, like this is percentage weight divided by 100. It's not working. Okay, have you noted this much? I'm erasing this thing. Okay, so another case is also there where this is represented as percentage weight divided by 100 into density into 1000 divided by molar mass. Okay, that's it. This is another formula. And so this formula is very simple actually. It looks very difficult, but when I'll do one question it will be simpler. Okay, first let me do the question of that simple molar mass formula. Okay, so the first let's do a question. Question is 9.8 gram of H2SO4 present in 2 liter of solution. Okay, this question I'm going to do. I'll do 3 questions related to this molarity so that you can understand this completely, all the formulas which I have written. The first formula, this simple formula, this is given mass by molar mass into 1 by volume. This question I'm doing so that you will be familiar with the questions. So the question is 9.8 gram of H2 SO4 is present in 2 liter of solution of this is solution. Okay, this is the question. So what we need to find? We need to find the molarity. This is so simple. So just write it as the formula given. So first thing is that 9.8. This is the given mass, 9.8. Now we get we'll have to get the molar mass of H2SO4. Molar mass of H2SO4 is 98. So just write 98 into this is volume. So volume is 1 by 2 liter. Liters also it is given. So just this is 10, then this will be 1 by 20. Okay, let me do it like this. So what will be the final answer? The final answer will be 0.2 moles per liter. Okay, this is the final answer. So I hope you have understood this. Now let's do that question related to density. Okay, density and percentage weight. So the question is density of H2SO4 is 1.5 and it is labeled with 49%. Calculate molarity of the solution. So what is this? So it is directly it is saying that density of H2SO4 is 1.5 and it is labeled with it is 49%. Okay, so we know that it is 49%. Now let's do this. So the formula which I said, this is completely applicable with that. So just write like this: 49 divided by 100 into your density is 1.5. So write that. Then what we need to write? Then multiply it with 1000 divided by the molar mass. So molar mass of H2SO4 now only we did 98. So 2 zeros will be cancelled out. Then 49, 2s are 98. Then here is no space. So the answer will be 7.5 mole. That's it. Next, this is mole per liter also you can write. This is not liter. Okay, so this is moles. That's the thing. That is 7.5 m. Next is another question which I'll discuss. That is that this is percentage is given. Here percentage was given and density also was given. But here percentage will be given and density will not be given. So how you will do that question? Okay, so that question I'll explain. This that is also very simple. Just look at here what I'm doing. This question is dealt like this. First let me tell you the question. Calculate molarity of 4% NaOH solution. That much is given. So you need to find these all. So how we can find? This is also very simple, don't worry. This is 4% of NaOH solution. That's it. And it has asked that calculate means find the molarity. That's it. So how can you find this? This is very simple actually. Okay, let me do this for you. What will happen is that whenever there will be density, you can note this point also. Whenever density is not given, then we need to consider the volume as 100 ml. Why we'll consider like this? Because percentage means 1 by 100. So here 4% means 4 by 100. Okay. 4% means 4 by 100. So volume we need to consider as this 100. So this will become very easy and very simple. Now see what will happen. This is just we need to do in the normal way. M equal to given mass. Given mass, this is 4 gram we know. Oh, it's not happening. Yeah, 4 gram divided by NaOH. So this is 40. The molecular mass of this is molar mass. Yeah, the molar mass of NaOH is 40. Then into this is B equals to 100 ml. We need to consider this in ml also. So it will be 1000 divided by 100. That's it. So 2 zeros cut, this is cut, this is 1. So the answer is how much? So the answer will be 1 m only. That's it. 1 m. So this is done, I think. I hope everything is clear now. Now let's go to molarity. Molarity is done now. Everything, this is only written which I have explained here. Now let's go to molality. What is molality? Actually this is not the last. In the last I will teach you normality also. So molality is what? Molality is the only term where solvent is used in the denominator. Otherwise in all the term solvent is not used. Everywhere solution has been used. But molarity is the only term where solvent is used. So you can completely remember this formula because this is like this, something different from others for that reason. So it is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by M. Okay, now I'll show you how to do this. See, moles, number of moles is written. This is also something we'll do like this. First let us derive all the formulas. So m here, this is small m, this is not in capital. M equals to moles of solute, we know. So it is moles of solute divided by mass of solvent in kg. Okay, that's it. So this is done, and we know moles is what? Given mass by molar mass. So what will the formula? The formula will be m equal to g m divided by mm or molar mass into 1 by mass of solvent in kg. So I know I am just writing like this, mass of solvent you have to write, okay, solvent in kg, that's it. Another formula also there, like that only, the same way we have written that, same way we will write this one also. Another formula is when given mass is given and molar mass is also given, but kg it's not, it's in gram, the mass is in gram, then what we'll do, we'll write here mass in gram, and here will in the see here will divide this 1000 divided by this gram. So for that reason we are doing this. When mass is in gram, we will do like this, given mass by molar mass into 1000 divided by gram, this mass. Okay. Next, another thing is also there, when we need to convert it into molarity, means molal. So what we need to do there, that time, let me erase this thing. Okay, that time what we need to do is that we need to do this thing, that molality. So I am not writing this much, m equals to 1000, that time molarity would be asked, okay, 1000 into molarity divided by, here one long term is there, 1000 minus, sorry, 1000 into density minus molarity into molar mass, that's it. Okay, so simple. This is the formula. I think you have understood this formula. Now I am doing a this question so that you can understand this formula better, in a better way. Okay, so the question is, see, the question is the density of 3 molar NaCl solution is 1.25 gram per mole, gram per ml, which is milliliter. Find molality. This is the question. So what is molality? Molality, oh, again I've tried to write this. Okay, I'll erase this. First let me write the question. So density of, so density we know, density equals to 1.25 gram per mole. Okay, then 3 molar NaCl solution is, so we know that this is 3, the molarity is 3. Then NaCl we know that it is 58.5, the molar mass is 58.5, that we need to keep in our mind, that it is 58.5. Now just according to formula, put the formula and get the answer, that's it. So what will be the answer? That will be, first thing is here written is the 1000 into molarity. So molarity is 3, then this is divided by 1000 into the density is 1.25, next minus here it is written that molarity into this molar mass. So what will write? 3 into 58.5, That's it. And I hope we got our answer. Just we need to do some calculation and we'll get it. Yeah. Next, we need to calculate this. This is 3000 divided by 1250 minus 175.5, and the answer is, here I will get the answer, just a minute. Yeah. And the answer is 2.79 molar. So you can also check this answer out if it is correct or not. Then let's do normality. Another thing is there which is not mentioned in the NCERT book, but we'll do this. This is normality. It is important also. So what is normality? Let me write this. Normality. What is that? Normality is the number of equivalent weight of solute divided volume of solution in liters. Okay. So what it is? It is number of equivalent weight of solute divided by volume of solution in liters. That's it. So this is all about it. Now let me do this. Actually it has a long formula. I don't think you have understood this in a once. So see, one thing is that first let me tell you what is equivalent weight. Number of equivalent weight. So number of equivalent weight means this thing, and there is no such space so that I can write it. So I am just writing like this, equivalent weight number, that's it. I am writing like this, just understand it. Okay, equals to this is weight of solute divided by equivalent weight, that's it. So it is weight of solute divided by equivalent weight. This is the formula of that, the equivalent weight. Then what is equivalent weight? That also we need to write. Equivalent weight is what? It is molecular weight divided by valency factor. So it is mm divided by the valency factor, or it is also known as n. Okay. So so many students have not been understood this, what I am telling all about. So now I will explain these things. This is actually the number of equivalent weight is actually the n factor or the valency factor. This is all about the basicity or the acidity. This thing, okay, now I'll show you what happens exactly. So just note down this formula, then I'll show you, and the final formula also I'll write. Okay, done. Here, so what is this exactly which I am talking about? So suppose let's take this example, H2SO4. Okay, how many hydrogens are there? 2 hydrogen are there, and we know this the molecular, so we are finding now the equivalent weight. So molecular weight is what? How much? Molecular weight of H2SO4 is 98. I have done these exercises now only. So it is the molecular mass equals to 98. Then equivalent weight will be how much? Equivalent weight will be how much? This will be molecular weight divided by the n factor. So 98 divided by how much H is present? 2. So we'll divide it by 2. That's it. And we will get the answer, that is 49. Okay. The answer is 49. Okay. This is the thing. Next, If you want to take another example also, I will take another example. Okay, let's take the example of NaOH. Okay, sodium hydroxide. So NaOH, what happens here? NaOH, what happens is that in NaOH there is one hydrogen atom. So we know that the molecular mass of NaOH is 40 and it has one hydrogen atom. So valency factor will be 1. So its equivalent weight will also be 40. That's it. So this is all about the equivalent weight. Now let me describe everything and short this formula. Okay. So as we written first that normality means number of equivalent weight of solute divided by volume of solution in liters. So this thing I need to write it again, that what the meaning of number of equivalent weight. So this thing I will write here, that N equals to given weight of solute, given weight divided by, this is of solute, divided by equivalent weight, this is also of solute, into 1 by volume of solution in liter, volume in liter. That's it. Okay, I hope you have got it. And the same thing will continue, that is 1000 by volume if it is in ml. Okay, and no formula else is there. Yeah, another formula is there, that is okay, let me erase this and I'll tell you. Wherever normality is compared with molarity, one formula come out, that is N equal to small n into molarity. Okay, molarity is big M. So small n means valence factor. Okay, which we got before also. Now let's do a question related to this thing, because before these given weight of solute divided by equivalent weight, this formula is easy and I hope you can do it. I think you do it. Then now I'm going to do this question, that normally, so the question is that normality of m by 20 solution of H2SO4. So means actually the question is m by 20 solution of H2SO4 is given, so what will be the normality of that? So if m by 20 solution of H2SO4, this is the question, H2SO4, that's it. The question is this much and we need to find the normality. So n equals to, as we know that n into m. Okay, so according to this formula what will happen, that see, so we know that it is H2SO4, so I think it will be 2, the valence factor will be 2 into m. Here m is m by 20, so this will be 10. Okay, so 10, so it will be m by 10. Now the normality is m by 10. That's it. Means m by 10 means the mole, this is 1 by m moles. So if we'll break down again, what will happen? Oh, it's left. So the answer will be actually this is, let us break it down, because ऐसे हम आंसर को नहीं छोड़ सकते हैं. So ये होगा 0.1. So this will be 0.1. That's it. Okay. So I hope you have understood everything and nothing else in left in the chapter. And whatever I left, please read it out, because whatever I left, it's for only you, that if I will read, then you cannot understand. I don't think about that. So this summary also important. Summary is all about the short, it is given in a short way, the whole chapter is given in the short way. So just read it out and thank you, it's done. Yeah, 2 things more also left here. So I just remember it now. Yeah, the 2 things are that wherever there will be molarity and molality asked about pure water, the answer will be 55.55. That's it. Okay, wherever there will be asked about molarity and molality of pure water, then it will be 55.55. And another fact also there, that is, this is all about the pure water. Okay, another thing is also there, that is temperature. When temperature rises in case of molarity, and in case of, okay, let me write this, molarity and normality, where there is volume involved. Okay, where there is volume involved in the this denominator, and these two cases, volume involved in denominator. So what will happen is that the temperature rises. When the temperature rises, these fall. Okay, this normality fall, and this molarity falls. Okay, this is all about this. When temperature will rise, molarity will come down, and similar case with the normality. Okay, so that's it, everything is done now. So thank you for your valuable time. Okay, please subscribe to my channel, and this is a series going on. Next I'll teach physics chapter 1. So everything like this I will go, and I'll teach 11th, 12th, the whole physics, chemistry and biology. Okay, so thank you.